Namaskar. A very good morning to you all. So, I'll be discussing the remote sensing of aerosols. This is day 2 of this workshop. Yesterday, we had learned about the basics, physics, and optics of aerosols, and then followed by the chemistry of aerosols and their health impacts. And finally, the day 1 ended with a session on aerosol forcing and boundary layer dynamics. So by now, you would have got an overview of what are the physics and chemistry of aerosols, plus what are their impacts both on climate, uh, air quality, as well as health. Okay, so today's day 2 will be dedicated to the measurement and the retrieval aspects. So first session I'll be taking, it will be oriented towards the physics and the retrieval of remote sensing of aerosols. So what we can do with remote sensing as a tool. Second session will be at 11:30 by Dr. Aditya Vash. There's a slight change in today's schedule because of the occupancy of some of the guest faculty. So, Dr. Aditya Vash from Ahmedabad University, he'll be discussing the ground-based instrumentation in the session on 11:30 to 12:30. Then we have third session by Dr. Narendra Roja. He is from PRL, Department of Space. He'll be taking you through the modeling aspects of aerosols. So his session will be at 1:45. Kindly please note this change. We will start at quarter to 2 and this session will end at 2:30, followed by the last session by Mr. Akhilesh Kumar from University of New South Wales, Sydney. He'll be giving you hands-on training on the aerosol products. The final concluding session will be the valedictory session, which will be held at 4 o'clock, chaired by Director IIRS. So I once again welcome you to the day 2 of this workshop. So let us try to understand the remote sensing aspects of aerosols. So by now you have learned in the previous all the sessions what are aerosols. I hope you now understand that these are the minute liquid or solid suspensions in the atmosphere. Okay, and because their sizes also vary, so we have categorized them into coarse, fine, and ultra fine, or you can say PM1, PM2.5, or PM10 particles. And we also understood yesterday that why should we care about aerosols, what is their impact on climate, air quality, and human health. So moving ahead, which aerosol properties does remote sensing enable us to study? So the two foremost and the very basic properties, physical properties, optical properties are aerosol optical depth. And this aerosol optical depth, yesterday Dr. Yogesh Kant has discussed with you in detail. As of today, you should, by now you should understand that AOD is the overall extinction. This gives you an overall extinction of light by the aerosol particles along the length of the atmospheric column. Now this atmospheric column can be nadir, vertical, or it can be aslant, but it has to be a vertical integrated column of the atmosphere. So total extinction by the atmosphere in the entire atmospheric column. But I hope you know that atmosphere is not overall same as you go from ground to the top. Yesterday we learned a lot about boundary layer dynamics. You could see that aerosol layers evolve over time and during seasons and at different geographical locations. So aerosols do vary vertically in the atmospheric column. So if you need to know the amount of extinction by the aerosols in different layers of the atmosphere or at different levels of the atmosphere, it is not the aerosol optical depth, it is actually the extinction coefficient. So extinction coefficient, using the basic physics laws of Beer's Lambert law, you can relate it with the total intensity and the extinction coefficient. So this extinction coefficient is exactly what which tells you the amount of light extinct by the aerosol particles at different layers of the atmosphere. So essentially, the extinction coefficient is measured at different layers or different levels of the atmosphere, whereas aerosol optical depth is the sum total or the integrated extinction coefficient or extinction by the aerosols. Okay, so these are the major aerosol properties which we can estimate using remote sensing. So going ahead, if the aerosol optical depth is high, so that means more sunlight is blocked, either due to absorption or due to scattering, but it is blocked. So there is more loading by the aerosol particles. Okay, so larger aerosol optical depth means you'll have hazy atmosphere, and smaller means you have clearer atmosphere. So apart from this optical depth and extinction coefficient, okay, we have several other physical and optical properties. Some of them have been already addressed in the first session, but because we are going to retrieve them from remote sensing, I'll just have a small overview, brief overview of these. So the other property is single scattering albedo. So this tells you, out of the total light which is extinct by the aerosols, how much is contributed due to scattering. So if you have particles which are more of the scattering nature, the value of SSA will be high. So it will be more scattering, means the ratio of scattering to the total is higher. Okay, so if you have absorbing particles, you will have smaller SSA. Okay, the third property which is of importance is asymmetry parameter. So in the very first session, in day one, we learned that particles scatter light, and they don't scatter light in only single direction. Their scattering may be in different multiple directions. So this is determined by the scattering angle, and this distribution is given by the phase function of the aerosols, and a parameter which tells you about whether it is a forward scattering dominated or backward scattering dominated, or it is a hemisphere, it is an equal scattering in the forward or backward direction. It is given by asymmetry parameter. More positive, that means more forward scattering. More negative means it's more towards backward scattering, and towards zero means light is isotropically scattered in all directions, backward as well as forward directions. Another parameter is angstrom exponent. This is very important because it tells you about the size of the aerosols. Okay, so how do we determine this? If we know the wavelength dependence of aerosol optical depth, we can find out the aerosol exponent. So if this exponent alpha is larger, means we are talking about smaller particles, and if it is smaller, means we are talking about the larger particles. So these are all optical depth, SSAs, asymmetry parameter, or angstrom exponent. These are all columnar properties, okay, as such given by either ground-based instrumentations or by remote sensing methods. Now, as we discussed about the extinction coefficient, which gives you the amount of aerosol extinction at different layers of the atmosphere. So connecting to that, another parameter is LIDAR ratio. So if I have a LIDAR and I can get the extinction coefficient at different altitudes of the atmosphere, I can also compute the LIDAR ratio. LIDAR ratio gives you information about how much is the light extinct with this and how much it is backscattered. So that means if we have higher LIDAR ratio, that means the light is less scattered or more absorbed. Okay, so because it is extinction coefficient to backscatter coefficient. So if the value is high, that means backscatter is low and absorption is high. Out of the total extinction, more extinction is due to absorption. So higher LIDAR ratio means these are highly absorbing particles. So you get this at different layers of the atmosphere or levels of the atmosphere. And low means you have highly scattering particles. Similarly, we have another. So LiDAR ratio has an analogy to the single scattering albedo. So single scattering albedo gives you the total columnar what fraction of light is scattered by the aerosols, and this LiDAR ratio tells you different altitudes of the atmosphere. So similar information. The last property which I would like to address is depolarization ratio. So that is also given by, if you have the polarized light. Okay, so what happens, suppose you send a polarized light and you have particles. If the particles preserve the polarization of the outgoing radiation, that means it's not altering it much, it preserves the polarization, so depolarization ratio is low, so it does not depolarize it much. And if this ratio is low, that means the particles we are talking about are spherical in nature. Okay, so this ratio tells you about the shape of the particles, spherical versus irregular. So higher is the depolarization, that means polarization is not getting preserved. The particles which is interacting with the light is of irregular shape, is non-spherical. Okay, so we get an idea about the shape of the particles also if we have an information on depolarization ratio. So these were the basic properties which we can retrieve, and I'm focusing towards remote sensing aspects only. So these are the major commonly retrieved properties. So uh, we have learned in the yesterday's session, entire session, that there are serious implications of aerosols on health as well as on climate. So how do we study them? How do we study their variability? Okay, so several types of instruments have been touched upon in the yesterday's session, depending on the use cases and test cases. Today in the second session, we will have a detailed information on what kind of instrumentations are being used. But on an overall perspective, so if we want to study their variability, the best way out is we use ground-based networks. Okay, we have global networks like Aeronet, MPLNet. We have regional networks like EarlyNet in Europe, ARFINet in India, etc. But the problem is you cannot cover the entire globe. These are highly accurate, but these are point based. Okay, they are limited in the continuous spatial coverage. You can't do that, though we can do that continuous monitoring in time. So the solution for us is remote sensing. So we are this remote sensing method enables us to have continuous spatial observation, especially using satellite remote sensing. So, but the issue is these observations or measurements are associated with retrieval uncertainties, but we get continuous spatial measurements. Okay, so what kind of satellite sensors do we have? We have, in general, we have two broad categorization. One is the passive sensing and the other is the active sensing. Passive sensing is when the source of illumination is not lying on the platform. On the platform, you only have a sensor. Now, the light from any natural or the artificial source illuminates the target. The target reflects or re-emits the absorbed energy. So that's a passive remote sensing method. And the other method is active remote sensing, where you send pulses of light. Okay, usually for aerosols we use lidars. So you send pulses of light, controlled illumination, and then you receive the backscattered energy again in the form of pulses. So that gives you information at different levels of the atmosphere. So there are several passive satellite sensors which have given continuous monitoring of aerosols over a large period of time. For example, AVHRR, then MODIS, VIIRS, then from India you have INSAT 3D, 3DR, and OceanSat, OCM2, OCM3, etc. So several satellite, Sentinel you have. So you have several passive based satellite remote sensing. inactive for a long time. Calypso used to operate, but then it was decommissioned, and then now we have measurements from early net, where you have UV LiDAR. We will discuss them. So the thing is, here from the passive sensor, you will have columnar variability. Okay, if you are sensing in a in a single direction, if you view using passive remote sensing from multiple angles, multiple viewing angles, then you can get some additional information on the elevated aerosol layers also. But on an average, you get a total column integrated measurements. But using the lidars, you can have vertically distributed aerosol properties. Okay, so now we focus on what are the factors which will affect the retrieval of atmospheric aerosols using satellite data. But before we go into that, we should understand in the atmosphere, majorly you have gases, then some amount of aerosols, and then clouds. So clouds we are not discussing here. The retrieval process is entirely different. But gases and aerosols. Okay, so what is the difference in the basic retrieval process of these two? See, the particles interact with the electromagnetic radiation in terms of absorption as well as scattering. And this, if you can see here, this is the atmospheric window description, where on the x-axis you have wavelength and on the y-axis you have transmission by the atmosphere. So you see at certain wavelength ranges the transmission is high, but at others there are dips. So wherever there are dips, that means those wavelength ranges are being absorbed by the atmosphere. These are not being allowed. So if I want to understand the variability of different gases in the atmosphere, I'll be looking at these dips. Okay, because the visible portion, if you look at the electromagnetic spectrum, if you see from here, this is largely unaffected by the atmospheric gases, except here where you have near ultraviolet or ultraviolet, where you have ozone. And but long wave radiation, if you see, it is more affected by absorption due to gases, for example carbon dioxide, water vapor, etc. All right, so for when we are going for gases retrieval, generally we are choosing the absorption dips region, whereas if we are looking at aerosols, these affect mainly the visible portion of the electromagnetic spectrum, and we need to consider both the absorption and the scattering aspects. So what are the aerosol signatures that we should be looking at? That will decide which kind of sensors I should be opting for my study. Okay, so if you look at the wavelength signatures, signatures means how uniquely you can identify a particular type of particle. Okay, in terms of wavelength here, if you look at these three pictures, you see on the x-axis I have wavelength, and on the y-axis, for the first picture, I have the ratio of aerosol optical depth normalized with respect to 550 nanometers, which is the reference wavelength generally we take for all the aerosol studies. So it is normalized with respect to that wavelength. The second picture, if you see, is the single scattering albedo. The third one, if you see, is asymmetry parameter. So if you recall the earlier context in this session, I had discussed the optical properties, aerosol optical depth, single scattering albedo. Optical depth will tell about the overall extinction by the total atmospheric column. SSA will tell you about the scattering or the absorbing type of aerosols, and G, that means the asymmetry parameter, will tell you about the phase function, or whether it is forward scattering or backward scattering. So if you see here, let us focus here itself in this shorter wavelength region. You can see that these three different types of aerosols which we have taken from Mishra et al. 2015. Here they have taken dust, polluted dust, and pollution. These three types of particles they have taken, and you can see that fairly in this shorter wavelength region, in terms of aerosol optical depth, these are easily separable. Similar is the case for SSA also, but the asymmetry parameter is similar for all these three. So if I am looking at the change in the asymmetry parameter, whether I'll be able to distinguish these aerosol types or not, I should be picking up these the other wavelength range, let's say from around 0 0.6 to around 2 micrometer. Whereas in shortwave region, up to the ultraviolet and the visible, if you see here, these are almost overlapping. These are the type of scattering these three are showing is not very much distinguishable. So that the whole idea of showing this to you is which wavelengths can separate which aerosol particles, and their properties will determine which wavelengths finally you will pick up for your remote sensing. Okay. Similarly, look at these two pictures here again. This is taken from earth.gsfc nasa.gov. They have shown mineral dust, sea spray, smoke, and suburban, these four type of particles. And in terms of AOD, they have plotted for different wavelengths. So if you see the you can separate sea spray and smoke from mineral dust and sea spray and suburban from mineral dust and smoke very easily, because these two are fairly separated from these two. But it's very difficult to separate the suburban from the sea spray, because these are behaving similar. But still, if you want to go for separating them, you can choose these wavelengths, 440 up to around 470 nanometers or so. Whereas if you go ahead, these become largely indistinguishable. Then there are crossover points also. At certain wavelengths, these two different types of aerosols are showing similar behavior in terms of their wavelengths, right? So uh, similar is the case for SSA. So you can look into the wavelength signatures which are published and which are given to public for different types of aerosols. You will get an idea that which wavelength ranges I should be choosing to work upon if I am targeting these 2 or 3 4 different types of aerosols. The other signature is in terms of polarization. So we had discussed the LiDAR ratio, which tells about the whether the particle absorbing or scattering at different layers of the atmosphere. So if the LiDAR ratio is large, it's mainly absorbing. And we also learnt about the depolarization ratio, which tells about the shape of the particle. So smaller depolarization ratio means spherical and larger towards non-spherical. So what we plotted here is, it's taken from Illingworth et al. 2015. You see this, if you see this marine type of aerosol particles, these are having smaller LiDAR ratios and smaller depolarization ratios. And these are easily distinguishable from, let's say, dust and smoke, or from volcanic ash, or from dusty mixtures, or from aged boreal biomass burning, right? So this is fairly distinguishable from all the different types of aerosols. Similar goes for volcanic ash. It's not overlapping with any of the clusters. Whereas if you see smoke, okay, look at only the smoke particles, the depolarization ratio is small. That means mostly these particles are spherical, but their LiDAR ratio is varying, and it's varying a lot. It's varying from roughly from 30 to around 100 if I take end to end. What does that mean? That means the type of scattering or absorbing characteristics of smoke is highly varying. Okay. And if you go to dust and smoke, this is a mixture. See, one is the particles only dominated by smoke. The other set of particles is dust mixed with smoke, dust and smoke mixture. So you see here, if you take this mixture, the entire regime shift from a smaller depolarization ratio to larger depolarization ratio takes place. So you now see that mixture is containing larger particles, and it's very much distinguishable from the single smoke particles, the individual smoke particles. You can easily distinguish these two. Whereas if you see dust and smoke, again there is a high change in their behavior. So that means if there is a mixture of different aerosol particles, that mixture itself behaves as another set of particles. Okay, you do not pre-assume that it will have the signatures of dust also and smoke also. It may totally behave as a separate entity, showing a different, totally altogether different behavior compared to its constituent particles. So this information comes from polarization signatures combined with the LiDAR ratio. Similarly, we can have an information on the asymmetry parameter also. Look at this graph. On the x-axis we have scattering angle. So scattering angle is varying, and here on the y-axis we have phase function, and we have plotted it for dust, soot, sea salt, sulfate, and then varying solar zenith angles and viewing angles. So SZA means solar zenith angle and VZA means the viewing angle. These dotted lines or straight lines, these correspond to the viewing geometry. So what you see is the if you have small angle scattering, that means you have forward scattering. Okay, this is often larger for the larger particles, the small angle scattering you can see from this dust, whereas the soot, which is a smaller particle, okay, the smaller particles are having smaller forward scattering. Okay, so the amount of scattering is also dependent, the amount and the direction of scattering is also dependent on the type of particles. So this information comes from the asymmetry parameter or the phase function or the variation of scattering in different directions by the aerosols. Okay, so what happens if we can combine, let's say we combine the polarization signatures also with the scattering signatures. So in the first picture, if you see here, we have fine mode particles here in the first two pictures, first and second, and here again we have two pictures for the coarse mode. Here what we have taken, we have a scattering angle and we have only one type of polarization, P11. So you see that different types of particles are largely showing similar behavior. But as soon as we added the depolarization or the polarization signatures here, we added another component also, P12. So you could see that all those six or five types of aerosols, these showed fairly separable properties. Same goes for the coarse mode particles, where the larger separation take place when you combine the polarization with the scattering. Why we want a separation? We want separation because we would like to identify different types of aerosols. Okay, how to do that? How do I distinguish that this is behavior is governed by which particle? I have to combine information on wavelength, on polarization, on LiDAR ratios, on scattering, on the phase function, etc. Okay, so the wavelength information gives you the discrimination of size, and it also gives you a discrimination from the surface component is large when we are considering the remote sensing signals. We will discuss on it in the coming session. Okay, then this is just I am summarizing, and then asymmetry tells you about whether it's a forward or backward scattering dominated particle. So it tells you about the size of particle and the type of particle also. Okay, and then we have single scattering albedo. This tells you about whether the particle is absorbing type or scattering type. So essentially it tells you what type of particle is there in terms of its composition. And then we have information on phase function, which tells you about again the type of particles, right? And polarization again tells you about the shape of the particle, spherical or non-spherical. Okay, so we have these informations coming in from wavelength, from asymmetry, from single scattering, and from polarization. We combine all this information to distinguish different aerosol types using remote sensing data. So the very basic question that arises to us is, From space, we are looking at the Earth's surface or any planet surface. Can we see the aerosols from space as such? Okay, so let us see this picture. This picture is taken over the Ganges, the Bay of Bengal region, and you can see that behind, over the background of surface, you have this haze, which is actually you can discern using the visible portion of spectrum also. Okay, so how, what is the challenge in separating the aerosol signal from the other signals coming to the sensor? See, what happens is when the light goes from surface, earth surface, to the sensor, it is coming from the surface, it is also coming from the atmosphere. Okay, and in the atmosphere it's coming from aerosols, it's coming from gases, it's coming from clouds. So these all contributions are going to the at sensor or the satellite sensor. So you have signals from surface and atmosphere. So we need to separate aerosol information. That means if I can estimate surface reflectance component well, if I can estimate clouds well, and if I can estimate gases very well, I can find out the aerosols from the total signal which is reaching. So the general aerosol retrieval process goes like this. You have top of atmosphere signals. Okay, signals means the top of atmosphere means the entire signal which is reaching the sensor. So we also call it as at sensor signal. So this at sensor signal is received in the form of digital numbers. It is recorded as digital numbers. We convert it into radians. We further convert this radiance to reflectance. But this reflectance is coming from the surface as well as the atmosphere. So we don't call it as actual reflectance of the ground. We call it as top of atmosphere reflectance. So this top of atmosphere reflectance is the signal that you have from the satellite data. This I am talking in terms of passive remote sensing. In active, we are talking in terms of backscatter. So I'll come to that also. So from that top of atmosphere reflectance signal, you screen if the pixel is dominated with cloud or snow. Okay, because these are highly reflecting targets, so it's very difficult to retrieve the aerosols beneath them, so we screen that data, and then we estimate what could be the amount of gases over that pixel, and that correction we do for gases. So now remaining is the surface contribution and the aerosol one. So then we do surface corrections. So for that you need to estimate the surface component also. And then we fit in the radiated transfer model, or we have pre-computed lookup tables, and which combines several combinations of, let's say, viewing angle, solar zenith angle, this much temperature, humidity, wind speed, etc., all the meteorological parameters, and different types of aerosol particles. So using that lookup table information, we fit the simulated top of atmosphere reflectance with the observations, and then from there we retrieve iteratively generally the aerosol information. So this is the overall aerosol retrieval process. The biggest challenge is the retrieval over land becomes very difficult compared to that of water, because on water the reflectance contribution by the surface is very small. Okay, so we can estimate gases easily, and we can negligibly give some value to the surface reflectance from the water, which is very low, and then we can estimate aerosols over the water bodies. But on the land, what happens is the surface reflection from the land itself is very, very high. So that mixes with the aerosol reflectance, and then the problem becomes complex. So what solutions we have? So I'm touching upon some of the operationally available retrieval methods. So there is one dark target approach, which is used by several sensors including MODIS, then VIIRS, etc. So dark target approach means we are looking in the generally in the visible spectral region, we are looking at those targets which are giving a darker background. For example, here if you see, it is the visible region. This is in the mid IR region. The surface here, the water body here behaves as dark target. Okay, and this on the land surface, this is very bright. But if you look at smoke here, if you look at the visible region again, you can see that this smoke becomes very hazy and visible over the dark vegetated background on the surface. So vegetation in the visible region appears as dark targets, especially in the blue and the red wavelength regions. So we estimate the aerosols only over the dark targets. We screen out the bright targets, so this retrieval will not happen over the bright targets, or even if you try to do that, will be essentially associated with larger uncertainties or errors. So you need to have the dark targets in the wavelength region that you are considering. So if this is there, then you can very well apply this approach. So dense dark vegetation is generally the land targets, dark targets in MODIS. But what to do when we have bright surfaces like deserts? So if you look at the spectral signatures of vegetation, soil and water here, you see here in this graph. So in the shorter wavelength regions around 412 nanometer, 410 nanometer, you'll see that this soil which is very bright, this appears dark. Okay, so the desert surface also becomes darker in certain wavelength regions, and these wavelength regions are towards the shorter or the deep blue, we call the deep blue wavelength regions. So here in MODIS that uses 412 nanometer, even CWIPS uses that same deep blue approach. So what we do is we screen out again the clouds, water, snow, ice pixels in vegetation. We only focus on the bright targets, and we estimate their surface reflectance in the deep blue wavelength channels using seasonal global database. Okay, so contributing that seasonal surface reflectance, we apply the retrieval algorithm. Okay, so the key takeaway is you use that channel where even the bright surface becomes dark. For example, it's shown here. If you see here in this red wavelength region, this is 412 nanometer. This is RGB. The first one is RGB 670, 555 and 412. So you have blue, green and red wavelength regions. And over this desert surface, it's very difficult to find where is the atmospheric haze or the aerosols compared to the background of desert dust. Whereas if you go to the deep blue channel, this all region which is the background surface, that becomes dark. So the brighter surfaces become dark and the aerosol reflectance can be retrieved from here, and then you can retrieve the aerosols. Okay, whereas this is not true if you go to the red channel 670 nanometer here. So there is a large mixing here. The aerosols were bright against the dark background of deep blue, but here these are mixing, the signatures are mixing with the background, so it's very difficult to do that retrieval here. So we choose the deep blue wavelengths. Now this was about a single viewing angle. Okay, so you choose dark target or deep blue. Now if you have a possibility of multiple viewing angles, for example we have MISR, so multi-angle and multi-wavelength approach is considered here. So you have multiple viewing angles. There are actually 9 viewing angles. If you can see here in this picture, you have 9 viewing angles, and for each viewing angle you have 4 spectral bands: blue, green, red and near infrared. So here you can tap the information of the angular dependence of scattered sunlight. Okay, and then you can estimate the different aerosol properties. Here you can estimate the size of aerosols also, the type of aerosols also, and the elevated smoke plumes also can be measured from here. And this was about multi-angle, multi-wavelength. Now we can have a single channel approach also. This we use in our INSAT 3D, 3DR, geostationary satellites. So what we do is, see, we only have single wavelength channel. Okay, visible spectral region, one channel. So what we do is, how do we attribute to the surface reflectance then? Okay, because in deep blue we went to that wavelength region where the bright surface became dark. Okay, so you tap that information of that wavelength. In dark targets you used the visible channels where the dense dark vegetation become the target, and the surface reflectance became lower, and you have taken that information. But what if you have a single wavelength channel? So here we in INSAT 3D we use previous 30-day radiance images, we compute the top of atmospheric reflectance, and we search for the second minima. So we find a clear composite image. Okay, so using this clear composite image, we take the monthly background aerosol climatology from MODIS, and we then find out the surface reflectance. Now once we have surface reflectance, then we use the lookup table approach and retrieve the AOD. So this approach is employed in INSAT 3D. Then we have the lidars. So here one example I've taken is from Calliope. So here what is done is, we have two wavelength channels, 532 nanometer and 1064 nanometer, and we have parallel as well as perpendicular polarized light. So what we do is, we emit the laser pulses. This pulse travels through the atmosphere, the particles scatter and absorb light, both things happen, and whatever is back scattered, it is received by the calypso. Okay, this was earlier operational, and then you split the information into different wavelength channels, here 532 and 1064, and in different polarizations. Then we use the noise corrections and calibration, and then we detect whether it's an aerosol or a cloud feature. What is the feature here? Okay, so then further we identify what type of aerosol layer it is, because now you have lidar ratio, you have depolarization ratio, you have extinction coefficient, you have backscatter coefficient, and you have information coming at different layers of the atmosphere. So you retrieve the total aerosol optical depth also, the extinction and backscatter profiles, vertical profiles also, you retrieve the lidar ratio also, you have the depolarization ratio also. Okay, so and we also have PACE aerosol remote sensing. This mission also currently operational. So here again, the PACE measurements are multi-sensor. Okay, multi-sensor means we have hyperspectral imaging, we have multi-angle polarimetry. Okay, and we have multispectral observations. So multispectral, multi-sensor, and multi-angle, all three included here. So we get the information on the aerosol loading, that means optical depth. We get information on the particle size from the spectral information, spectral channels we have. We get the information on the refractive index and the non-sphericity or sphericity of the particle using the polarization information which is there. We also come to know about the particle shape by knowing the asymmetry parameter or the angular dependence or the scattering angle information. So we have multiple retrieved aerosol products. We have AOD, we have angstrom exponent, we have fine mode fraction, we have single scattering albedo, we have refractive index complex. Okay, we have a particle size distribution also, and we have different aerosol types. Okay, so all this several aerosol information is getting retrieved here. Then we also have an operational earth care system, the mission, where we have a lidar which is measuring the backscatter profile as Calypso was doing, but now this is doing in the UV region. Okay, 355 nanometer is the wavelength region, and with a very high vertical resolution, 100 meter or so, it gives you the vertical resolution of aerosols. And then we have a radar also complementing the LiDAR at it's giving the vertical resolution of 480 meter, so, and it's operating at 94 gigahertz. Okay, so this is giving this information is coming from the radar. Then along with LiDAR and radar, we also have an imager. So an imager will give you the total columnar properties. Okay, no vertical resolution given by LiDARs or radars, but imager, multispectral imager, which is there, that gives you information on aerosol optical depth, because it is in different wavelengths, so it gives you angstrom exponent, it gives you aerosol types, etc. And we also have a broadband radiometer, which gives radiative fluxes or heating rates or energy balance. So it's a mix of multiple instruments. You have active sensors also here. These are providing the vertical profiles. You have passive sensors also here, which are providing the column integrated information. So this provides high vertical resolution, wide swath coverage also, because you have imager and radiometer. See, the one issue with LiDARs or radars for atmospheric sensing is the swath will be limited, the footprint will be limited, which is not a limit with the imagers. So you have wider swath coverage with the imagers, and you can have a comprehensive aerosol measurement. Okay, so using all these passive sensors, active sensors, a combination of different spectral channels, different viewing angles, okay, using LiDARs, using radars, using different polarizations, you can have a multi-scale observation, you can have an integrated analysis, you can have finally the actionable insights, as yesterday Professor Sagnik Dev was showing you the daily or the hourly PM 2.5 maps, which are possible now using a multitude of different information. Okay, so you can have global monitoring also at national scale also, and at regional or local scale also. I'm not going into too much of the case studies, but I've given you an overview of what kind of sensors are available in remote sensing, satellite remote sensing in particular. Okay, so this out of this entire aerosol retrieval process, the most tricky one is the surface corrections. Okay, as we did with deep blue or dark target, or using the climatology, etc. But we at IIRS have developed a simple physics-based approximate model, which is not which is not using any lookup table approach or any online radiative transfer simulations. It's using an approximate physics-based model, and we are using different spectral channels, and we have also created software based on this approach, which is called IAOD software. We have used the approximations for radiative transfer model, and we have used approximations for surface reflectance. So we have not done any atmospheric correction per se. We have not specifically targeted some particular features like bright target or dark target, etc. We have the algorithm is not sensitive to which particular wavelength it will perform well. We have tested it with multiple spectral channels, with multiple sensors, and it's working well. It's a generalized model, and for if for an understanding based perspective, you can have a look at it and you can use it. And this has been published. There's a copyright that we have got. So this is the overall view of the software. We have a small video which will be shown by Mr. Akhilesh Kumar in the last session of this day 2, where you will get an idea what all functionalities are there. Okay, so this was about the physics-based retrieval. See, remote sensing enables physics-based statistical retrievals, but we also have a scope for machine learning or deep learning based retrievals, which are picking up momentum these days. Okay, so what we do in this method is the input layers to your model are coming from satellites, for example, MODIS or VIIRS or Sentinel 5P or Calypso. You can use EarthCare, you can use PACE, you can use CWIFs, and you can use multiple layers of the inputs, and you can supplement this with the ancillary data. For example, you can give meteorological information, you can give LULC information, you can give the DEM information, the slope and aspect information, you can tell about the solar zenith angle, viewing geometry, and you can tell about all the ancillary data you can supplement with your input satellite data. And for training and for validation, you supplement it with the ground measurements also. It can come from Aeronet, it can come from EarlyNet, it can come from CPCB, it can come from ArfiNet, or if you have your own station monitoring, you can give that information also. So once you have input layers ready, then you have your methodological pipeline. So first you ingest your data, so you collect these multi-sensor data, then you co-locate them, resample them, because they will be at different resolutions. Okay, so co-location and then resampling, spatiotemporally resampling, this part you do. Then you do the quality assessment, you filter out the bad quality pixel data, and you make your data ready. So once your data is ready, you pre-process your data, you do screening, you do cloud masking, snow masking. If there are large unfilled data, I mean, for example, in winter region, in winter season on Indian region, if you see, lots of pixels will be dominated by clouds which will be empty after you screen from the clouds. So what do you do for that? You do gap filling. Yesterday also Dr. They was showing one such image where they have gap filled and the lots of empty spaces in the data. So you do gap filling, you remove the noise, you may require to do normalization or standardization because you are dealing with multiple parameters. So you can normalize, then things becomes little easier. So you have pre-processed the data. Then comes the feature engineering part. So you have several spectral features, you have several atmospheric features, you have several surface features, you have several temporal features, and you can have different spatial context. That means you can have different averaging moving windows. Okay, so you do a feature engineering here. Then once this is done, you understand which feature is contributing most to your model. Then you have your models. You can have the single standalone models like XGBoost or Random Forest, CNN, etc. You can have ensemble of these, and then you target whether you want to retrieve AOD, AAOD, AE, SSA, G, etc. Whatever you want to, or PM 2.5. Then lastly, once you have modeled your data, you have trained your model, you put physical constraints, you put some range limits, you can keep consistency checks, and then once you have retrieved your data using machine learning or deep learning pipeline, then you validate and do an uncertainty estimation. So a large part of aerosol remote sensing is moving towards AI/ML these days. But there are limitations and challenges with both physics and machine-based, learning-based aerosol retrieval. The physics-based aerosol retrieval, it requires the accurate modeling of radiative transfer. Okay, and there are several assumptions involved. Whereas in the machine learning based retrievals, you should have your data quality should be high quality, and you should have labeled data sets if you want to go for training. Okay, so there are challenges in both. Okay, the physics based result retrieval is becomes computationally very challenging if you integrate polarization also, multi angles also, multi wavelengths also. Okay, and multi sensors also, it becomes very challenging. Okay, but in machine learning also you have a risk of overfitting. So there may be poor generalization. You may be proposing a model which is fitting very well to your particular region, but it may fail if you go to another region. So with these, both of them have their challenges, both of them have their limitations, and we should, if possible, we can try compromise. We can try adding the physics informed machine learning in the future aerosol studies. Okay, so with this, I thank you all, and we can break here for 2-3 minutes. Then I can take some of your questions. Okay, so welcome back. Let me take some of your queries. So, Raghavi is asking, in practical remote sensing applications, when should we prefer physics based retrieval methods over machine learning methods? Okay, and also, how do we decide which approach is more appropriate? So, what happens is, if you talk about physics based methods, these are actually highly reliable and accurate. If at all your assumptions, see, you have to make large assumptions, you don't have measurements of every parameter with you, still you want to retrieve aerosol properties. Ideally what you should have is, at the same time when you're capturing the total signals, you should have the information on the entire meteorology, the entire surface properties, the amount of gases at different layers of the atmosphere, etc. So ideally, if your assumptions are very close to the reality, which you are doing in case of physics based retrieval, then your physics based retrieval becomes very accurate, highly reliable. But when your surface reflectance retrieval becomes quite complex, and when several iterations are required, so it becomes highly computationally expensive, and several times you don't have correct assumptions for, let's say you have an aerosol regime where there's a large amount of mixing and there is large amount of uncertainty in making the assumptions. Better is you switch to the machine learning approach. Okay, so machine learning will give you a faster retrieval, a large area retrieval, and then, but in machine learning, generalizability may be an issue, because maybe you are training your model and it's overfitting to your particular region, but it may fail in the other region. So that care you need to take. Okay, you can go for approaches like loro, leave one region out, like that. But I would recommend the research now which is moving, it should be hybrid approach, it should be informed by physics or constrained by physics, and it can be machine learning approach. So physics informed, PINN we call it, or the physics constrained or the hybrid approaches would be my suggestion. Okay, so Sandhya has also asked the same question. I hope I answered. Okay. Okay. The another question is, since Calliope, okay, relies on preset lookup tables, yes, how frequently do mixed layers of dust and pollution over India cause the algorithm to choose an incorrect LiDAR ratio? This is, yes, this is a big issue. In fact, see, Calypso is using a categorical classification algorithm. Okay, if there is a mixing, the choice of LiDAR ratio can be highly incorrect. And you can refer to published work where Calypso's retrievals have been compared with respect to the high quality or the high precision retrievals by HSRL. Okay, and there they have discussed in depth what happens when there is mixing in these different regimes and what is the impact on the choice of the incorrect ratios. Yes, this is an issue. I agree with you. So Abhijit is saying, so we can easily understand weather condition and predict weather using aerosol property or using satellite space LiDAR image. I do not understand your question, Abhijit. Maybe if you wish to talk about the numerical weather prediction models or the WRF models, maybe you're asking. We have a detailed session by Dr. Narendra Ojha, where he will be discussing on the modeling of aerosols, the limitations and the requirements and the challenges also. You can have we can have a detailed discussion here, but yes, these there are uncertainties in the inputs will lead to the modeled errors also. Then Sandhya is asking which is more important for aerosol retrieval, multi-angle measurements or multi-wavelength measurements. See, multi-wavelength is the first requirement. We should go for multi-wavelength at least, because you have a single sensor and you have to just pass the signal, filter it to different wavelengths. That is the first thing that you should always have. And you will see that most of the channels in the passive remote sensing instruments, satellite instruments, these are multi wavelength instruments, because that will enable at least even the total aerosol optical depth. And it not only for the aerosol information, but it also helps you to estimate the surface reflectance. See, surface reflectance you may estimate if you have a multiple wavelength channels easily. You can that your challenge is slightly reduced if you have multi wavelength approach. So multi wavelength is the first thing. Second comes multi angle, because multi angle what you need to do is you have to mount multiple sensors in multiple viewing angles. So that's a cost incur in the overall platform system also. So if you have multiple angles, that gives you information on something called BRDF, bidirectional reflectance distribution function. And you, because you are slicing the atmosphere in different directions, even if you don't have a LiDAR, you have a passive remote sensing payload, then also you get an information on the shape of the or the type of the aerosol particles, as well as if there are some elevated aerosol layers. That information also can be broken down if you have multi angle. So as I said, you keep on adding the dimensionality in terms of its signature. You have wavelength, you get one information. You add angles, you get another information. You add polarization also, you supplement your information. You have lidars or radars also, then you further strengthen your information, right? Okay. So, why light behave differently in space and in Earth? I don't understand again this question. Light, see, light is interacting. Light is energy, and energy is interacting. So, if it is passing through vacuum, there are no interactions, because largely there are no particles. If you are traveling through the space, okay, so your large portion is coming through the vacuum, so it is unaltered. As soon as the light sees a particle, okay, even if it is a very shallow layer of particles, then also there will be an interaction. As soon as there is an interaction, it can be in terms of absorption or it can be in terms of scattering. Okay, so once it is absorbing some radiation, it can be used in terms of its vibrational, rotational, or electronic transitions. Accordingly, you will have re-emissions. Okay, so absorptions will be manifested as re-emissions. And once you have scattering means redirection. So light may change its direction. And this scattering can be elastic or inelastic. Elastic means the outgoing radiation which might have altered its direction. It may go in the same path also, it may go back, it may take a different route. So there is redirection, but this redirection, if it is accompanied with a change in its wavelength or frequency, this is called inelastic scattering. For example, what you study in Raman's scattering. Whereas if the light's frequency is unaltered after scattering, which is large part of the scattering is dominated by elastic scattering, and there is no change in the wavelength of outgoing and in the incoming, then for example you have Rayleigh scattering, you have Mie scattering. So this comes in the bracket of elastic scattering. So as soon as the light sees particles, be it dust in the atmosphere of a planet or the cosmic dust, whenever there is an interaction, there will be an absorption. there will be a scattering. Okay, so what type of scattering, what type of absorption will be determined by which wavelength was interacting with which type of particle. Okay, I hope I answered your question. Okay, so there's a question on how do ground-based sky radiometers handle the loss of polarization sensitivity. No, they don't lose the polarization sensitivity at very low or very high scattering angles near the solar earlier. Okay, so see, if you're talking about the ground-based sun or sky radiometers, for example, CIML, which is used in Aeronet, or the polarized variations of PON sensor series, they do not lose polarimetric sensitivity at smaller or large scattering angles. Instead, they are designed in a way that they should be able to account for a drastic change in the atmospheric degree of linear polarization, coupled with there could be high susceptibility to the stray light, and there could be alignment errors. Okay, so they do account for the very high or large or small scattering angles. So Shivangi is asking which software is this for analyzing satellite data for air pollutants, wavelength signatures. Are you asking about the IAOD software, which this is an indigenous software developed at IIRS. We have developed it, and this retrieves the aerosol optical depth from multiple channels. You can give multiple channels of multiple satellites. Okay, so with this, yeah, so with this, I think I stop here, and the next session now will be at 11:30 by Dr. Aditya Vash. Okay, so stay tuned till that time, take a break, and we will be right back at 11:30. Okay, thank you. Welcome back to the second session on day 2. We have with us Dr. Aditya Vaish from Ahmedabad University, and it gives me great pleasure to introduce him to you all. Dr. Aditya is an atmospheric physicist whose research spans across aerosol instrumentation, air quality, climate change, aerosol radiation interactions, and development of lightweight atmospheric sensors. His work combines observational measurements and instrumentation development to improve our understanding of atmospheric aerosols and their environmental impacts. Prior to joining Ahmedabad University, he had been associated with SAC Ahmedabad as well as VSSC ISRO. Dr. Aditya, we are privileged to have you here with us. Thank you so much for joining us. Now, over to you.
Yeah, thanks very much. And I look forward to this wonderful interaction. Okay, so good morning, all. And as you can see, the topic for this session is aerosol measurements, retrieval, and impacts. Specifically, I will be talking about ground-based aerosol instrumentation. So I was looking at the previous sessions, and I think by now all of you are aware of the fundamentals of aerosols and their different properties. Still, in order to uh, make the continuity, I will give a brief background about what are these particles. So as you all know, aerosols are dispersion of solid and liquid particles. They are suspended in the air. They are everywhere. We inhale them, we exhale them. They have very diverse properties. They come in different size range, they come with different colors, they have different chemical properties, as well as optical properties, or light scattering or light interaction properties. If you have to look them, I mean, they are invisible to naked eye. They are so small, but if you look at them through a microscope or electron microscope, this is how they will, some of them will look like. They can be pretty dark in color. They can be long chain agglomerates. They can be spherical in shape. They can be metallic in nature or can be cuboidal and so on. They can also look like this. These are fungal spores and bacteria or salt particles which are in the monsoon season, in the present season, they absorb water and grow in size. Okay. So as you can see from this image itself, they come in varieties of shapes and sizes. And that's why it is very challenging to measure each and every of their properties using a single instrument or using a limited set of instruments. Okay, so what are their properties we are talking about? So we can classify the properties of aerosols into three broad categories. The physical properties is specifically the number, concentration, size distribution, the growth of these particles under changing environmental conditions, specifically humidity, and also the physical mass of these particles. Now, all of these parameters except for the growth are what we call the bulk parameters, okay? And there are individual instruments to measure each one of these properties. Then we come to optical properties. In the optical properties, the primary ones are the scattering coefficient, absorption coefficient, the optical thickness of these in the atmosphere, as well as the enhancement, scattering enhancement due to the growth of these, physical growth of these particles. And finally, the chemical properties of these particles, what they are made up of. They are made up of salt or organics or carbon and so on and so on. Are they primary particles or secondary? Primary means are they directly emitted from the source, like for example, wind generated dust or something, or are they formed in the atmosphere through some different chemical processes? Okay. Now, all of these properties are directly measured using a set of instruments. However, based on these primary properties, we can also derive additional properties of aerosols. For example, from the physical properties, we can also have the fine and coarse mode fractions. We can, from the bulk mass, we can talk about PM1, PM2.5, PM10 mass. We can also talk about, single aerosol particle versus an aerosol particle which is coated with an external species, so core, cell thickness, and so on. The angstrom exponents which tell us roughly the size mode of these particles, are they coarse, are they fine mode, and so on. Likewise, from the primary optical properties, we can define auxiliary parameters, for example, the single scattering albedo, which indicates how much scattering is there with reference to extinction. Asymmetry parameter, again forward to total scattering ratios. Phase function, how much scattering and extinction is happening in which direction. So it's a directional property. And the refractive index, scattering versus absorption. The real versus imaginary part of the refractive index gives us those ideas and also indicate something about the chemistry. And finally, from the chemical, we can also derive organic carbon to elemental carbon ratios, water soluble fractions, and if there are metals, and so on, so on. Again, the central column indicates that these properties are there which can be measured directly using an instrument. And the third column, these properties are which usually we derive using the primary properties, except for PM1, 2.5, and 10, which we can directly measure. Okay, so we can again broadly classify these aerosol properties and how do we measure them into two different broad categories. So we can measure these aerosol properties either in situ or using remote sensing technique. Now, when we talk about in situ, again, we can have offline measurements or we can have online measurements. So with offline measurements, we primarily mean filter-based measurements. We sample aerosols on a filter substrate and then subsequently do physical analysis, chemical analysis, and so on of that. Then using online techniques. Online is real time. Okay, so the instrument is inhaling the ambient air, taking aerosols from the outside, and in real time giving different properties, be it a scattering coefficient or the mass or the chemical speciation of aerosols. Now, in the remote sensing regime, we can have satellite-based remote sensing and ground-based remote sensing. So satellite-based, I think all of you are aware of, and there were different talks around this. So we have many satellites from the Indian Space Research Organization, Earth observing satellites. You have INSAT series, then you have Ocean Color Monitor, OCM series, and so on, which using which we can derive different aerosol properties. And then you have satellites from other countries, other space agencies, for example, ESA, NASA, and JAXA. You have satellites like Calypso and then MODIS, which can give different properties of it. So I'll briefly talk about some of those later. Then ground-based remote sensing, we have instruments which primarily measure optical properties of aerosols. So let me dive further into that. So in the remote sensing, as I said, we can have satellite-based and ground-based, and they measure primarily the fine mode fraction of aerosols, the angstrom exponent and aerosol layer height. So specifically, LiDARs are instruments using which we can measure the aerosol layer height, we can measure the depolarization ratio and so on. Then using satellite remote sensing, we can also find out fine mode fraction and angstrom exponent. Then in the optical properties, we can measure the optical thickness. So there are a multitude of instruments which are available to measure optical thickness using satellite-based as well as ground-based. So in the ground-based, one of the primary measurement instrument is the MWR, multi-wavelength radiometer, which was developed by Space Physics Laboratory, SPL, in VSSA. And they have a network of stations called the RF network. So using that, they measure the aerosol optical properties at different stations. So it's a ground-based remote sensing-based technique, and it's a passive technique. So in the morning, the instrument will wake up and then will track the sun, and based on the light attenuation technique, it will measure the optical thickness. Then we have using ground-based LiDARs and so on, we can measure the depolarization ratio, which tells us about the physical nature of aerosol, whether it is spherical or aspherical in nature. Using LiDARs, either satellite-based or ground-based, we can also talk about vertical extinction profiles. So if we integrate the vertical extinction profile, we get the optical thickness. And if we get it layer by layer, then we have the extinction. Okay? And finally, we get the absorption aerosol index using two different wavelengths, one in the both in the near UV or one in the near and one in the mid UV, and we take the ratios or extinction ratios of those wavelengths, and we get the absorption aerosol index, which indicates uh, how much absorption potency is there in the aerosols, or the aerosol atmosphere in general is scattering in nature or absorbing in nature. For example, the western part of India, which is where the Thar desert is, in the summer due to wind activity, a lot of dust is there in the atmosphere, so the absorption aerosol index will be in general higher in these regions. Okay, coming back to the remote sensing and chemical properties, uh, there is not much, in the chemical properties which remote sensing measurements currently can do, but still using spectral remote sensing techniques, we can broadly classify aerosols. We can specifically talk about their categorization based on their broad chemical signatures, like whether they are the bulk of them are dust, or they are salt particles, or they are scattering in nature or absorbing in nature. Not much has been done in terms of chemical properties of aerosols using remote sensing techniques, either satellite or ground based. Now, coming back to the in situ properties or in situ measurements. So in the in situ, we have different techniques, online as well as offline. So in the online, when we talk about physical properties, we have instruments which can measure the aerosol number concentration in real time. So how many number of aerosol particles are there in a given volume of air, size distribution, uh, total mass of aerosols, as well as segregated mass like PM1, 2.5, and 10. Fine mode fraction, so relative dominance of fine particles versus coarse particles, and so on. And the angstrom exponent, which is kind of indicates again the dominance of fine or coarse, or indicates the size, dominant size mode of particles. In the optical properties, we have instruments which can measure the total extinction, spectral scattering coefficient, and backscattering coefficient. We have instruments which measure in real time the absorption as well as single scattering, single scattering albedo, and the scattering enhancement. And finally, in the chemical, we have instruments which give us in real time non-refractory composition of aerosols, black carbon concentration, which is one of the key constituents of aerosol properties in urban regions. And black carbon, as you know, is emitted by incomplete combustion processes in the atmosphere. And it is one of the most potent aerosols for which causes warming. So bulk of the aerosol species, as you know, cause cooling of the atmosphere. However, the carbon species, black carbon species, they cause warming, so they offset the cooling by aerosols. And then finally, bulk chemical speciated mass. So these are all about the online techniques. In the offline, we have, for the physical properties, we have mass size distribution. So we have filter-based measurements where on a filter substrate, we collect aerosols for a given duration. So since the concentration of aerosols in the atmosphere is very less, ranging in nanograms to micrograms, and looking at the sensitivity of instruments, we need to have measurement time somewhere between 6 to 18 to 24 hours. And in remote regions like the Himalayas or the Arctic or the Antarctic, it can even be more than 24 hours to get a detectable mass of aerosol, which can indicate some signal on the instrument. Okay, so you have a filter substrate. We collect aerosols on that for 24 hours, and then we weigh them on a weighing balance. The weighing balance has to be sensitive enough to detect. So that's why offline techniques can't give you real-time values of mass. Then in the optical, we don't have any dominant offline measurement which gives us optical properties, even though there are some indirect techniques, but I'm not diving into that. Then chemical, of course. So once you have the filter measurements, you take those filter measurements and you do subsequent chemical analysis. Again, this is offline. So, and these techniques can take anywhere between few days to few weeks to months. So that's why you don't have, again, any real-time measurement of mass or chemical properties using offline techniques. So offline techniques have definitely some advantage over online techniques. For example, if you want to understand the bulk nature of Earth over a longer period of time, offline techniques are much better. If you want to understand aerosols in regions which have very, very less concentrations, then many times online techniques might not help because of the very feeble concentrations, and you need very longer integration time. So in those cases, also the offline techniques would be of great help. Okay. Now, so by now, I think it is aptly clear to all of you that a single instrument can't measure all of these multitude of aerosol properties, be it physical, optical, or chemical. So definitely we need a suite of instruments to characterize the ambient atmosphere or ambient aerosols. And but then there are challenges. So what are the challenges? One of the most prominent challenge is the sheer size and concentration of aerosols in the atmosphere. So if you look at this graph, on the x-axis you have size of aerosols starting from roughly 1 nanometer. So this is transition between gases to aerosol regime or particulate regime. So roughly from 3 nanometers, I'll say, going upwards to thousands of nanometers. So the aerosol size spans roughly 5 orders of magnitude. Now, if you're not able to comprehend what does it mean, think about a glass marble, the small glass pebble, which we used to play during our childhood time. If you take that glass marble and think of that as 1 nanometer size, and then drag this glass marble on the x-axis. So once you're here, that's the unit of glass marble. You drag it to 10, it means it increases in size 10 times. You go to 100, it means that single particle, glass marble, is now 100 times of the original size. Likewise, 1,000 times, 10,000 times, and 100,000 times. So it can be the smallest particle in the atmosphere. If it is of the size of a glass marble, then the largest can be the size of a city like Delhi. So you cannot think of a single instrument which can measure this entire size range. So if I have a measuring tape, I can measure the length of a table, the length of a room probably, or I mean, at the most the length of a hall, not more than that. With a vernier caliper, I can measure the length of or thickness or length of very, minuscule things. But then if I have to measure the height of the building, the size of the city or something, I need different tools. I need to use different techniques. So that's why it is challenging for a single instrument to measure this, 5 orders of magnitude size distribution. Second, the number concentration. Number concentrations of aerosols span roughly tens of orders of magnitude. So if you look at the y-axis, that's a particle number concentration. Uh, as low as 10 power minus 3, 10 power minus 4, as high as 10 power 5, 10 power 6, or even in many cases probably up to 10 power 7 as well. However, very rare. Now, if you have some instrument which can measure, let us say 10 power 2, 10 power 3 orders of magnitude concentration, the same instrument might not be able to measure very high or very low concentrations because of the sensitivity issues. For example, if you think of a simple weighing balance, right, it will have a range. Let us say it can measure from uh, 10 grams to 5 kilograms, right? If you have to measure less than 10 grams, then you need a more sophisticated weighing balance where the range is probably zero point 0.1 gram and so on. If to measure higher than 5 kilograms, you need a bigger weighing scale where the least count or the resolution can be probably 100 grams or can be probably zero point 0.5 kilograms or something, right? So again, the same concept applies to particle numbers. The same concept applies to particle mass and particle size and so on. So this is one of the challenge why we need for each of these modes, nucleation mode, fine mode, accumulation mode, and coarse mode part, we need a different set of instruments to measure their physical properties, to measure their optical properties, and in some cases also their chemical properties, specifically for nucleation mode aerosols. Now, another aspect, another challenge is how do we measure aerosol particles? we are talking about ground-based aerosol instrumentation, ground-based measurements. So for that, either I take my instrument out in the field. uh, these instruments can cost dearly. They can run into several crores of rupees, right? So I can't just leave them outside because of the weathering, intense sun, heat, rain, and so on. So instruments might just go bad. So I need to keep my instruments inside a secure chamber, uh, where environmental conditions are stable. In the sense, I can control the temperature, I can control the humidity. I know that there is no cross ventilation, no wind flowing, and so on. Why that is required is because these are very, very sensitive measurements. So once I do that, the challenge is I need to bring these particles, aerosols, from outside, from the ambient to the lab, right? So how do I bring the particles from outside to the lab? I need a tube for that. Now, the moment I think of a sampling inlet or a tube, then naturally there are losses of particles. Natural losses, coagulation, diffusion, and sedimentation. So coagulation means these particles coagulate, they stick to each other and then grow in size. They diffuse, so they hit the, very small particles. They will literally stick to the walls of these tubes and just get vanished. And sedimentation is due to gravity and due to inertia, larger particles will literally sediment on the wall of the tube, right? So these are natural losses. Then there are sampling losses. So I need to ensure that the flow which is coming to the lab, the air flow, is laminar. It means all the flow lines are parallel to each other and it is not turbulent, because the moment there is turbulence, there will be turbulent inertial deposition. Particles will collide with the walls of the chamber and then they will deposit in the tube. There can be inertial deposition in the bend. So if the tube is bending anywhere, due to inertia, larger particles will try to go straight and then they will hit the wall and so on. So this schematic by Wyden is clear some of those aspects. So significant particle losses happen when we try to sample ambient air. So there are losses due to subisokinetic or super isokinetic sampling. Then you see this contraction here, right? So larger particles, due to their inertia, they will try to go straight, whereas the flow is trying to turn, and these particles will literally hit the chamber wall, right? And they will be removed from the overall concentration. So this is what we call inertial deposition in the contraction. Then there's a bend here, and again the particles will hit. Larger particles cannot go with the flow due to their inertia. They will try to, as per Newton's law, they will try to go in the straight line or go in their defined trajectory. So again there will be deposition. Then diffusion losses will be there. Very, very small particles, they will simply stick to the wall and then they will diffuse. If there is turbulence or eddies forming within the tubes, inertial depositions will be there. Due to, if the tubes are horizontal, due to gravity, larger particles will try to settle down. Sedimentation losses are there. So many different mechanisms are there to artificially remove the particles. So when these particles are artificially removed, then we are actually not measuring the true properties of these particles. So we need to overcome these set of challenges, be it of different orders of magnitude of size and concentrations, or losses in different segments of the instrument or of the sampling inlet, right? Now coming to the sampling inlet. So there are many different kinds of sampling inlets. The primary property or the primary task for this sampling inlet is to bring aerosol particles from the ambient to the lab. So this is one of the most popular sampling inlet. This is what we call the PM10 or PM2.5 impactor inlet. And these are what we call the cyclone inlet. So what is happening here is there's an airflow and aerosols are entering through this node, and due to the physical construction, the nature of this cyclone inlet, the flow will go in a spiral way down, and larger particles will try to come out of this, and smaller particles, because of the flow, some part of the fraction of the flow will go up, they will just spiral out of this, right? So if we design it carefully and if we define a specific flow and do the right calculations, we can decide which size of particles we will get here and which size of particles will get on the top here. Likewise, in this inlets, there's an impactor plate here. So as the flow, depending on the flow, each particle will have a specific inertia and velocity. And there's an impactor plate, the flow will go down, and then there's a U-turn for the flow. So the larger particles, due to their inertia, they will continue to go downwards and hit the impactor plates. The smaller particles will go up and then go from the side bend and finally to the sampling instrument. Okay. So this is one technique to segregate particles or to bring particles from ambient to the lab. There are multitude of sampling inlets I'm not diving into, but in cold regions we have heated inlet. Then when there are regions which are very windy, or let us say if you want to sample aerosols on an aircraft, right? Then you need an isokinetic inlet which ensures laminar flow of aerosols at varying wind speed and so on. So coming to the physical properties, again, as you have seen already that there are plethora of properties, physical, optical, and chemical within each. Then there are multitude of sub properties of a resource, and definitely it is not possible to cover each and every instrument or each and every property, but I'm trying to tick box some of the most important and some of the most popular instruments as well as measurements. Now, when you look at this size, this graph, what you see is there are different modes of aerosol particles, and these different modes emanate from different processes in the atmosphere, right? So, coarse mode particles are usually generated through mechanical processes. Fine mode particles are usually generated using combustion processes. Nucleation mode, as the term itself indicates, that they are nucleated, they take birth in the atmosphere directly or through gas to particle conversion. And then from the nucleation, many of these particles coagulate, they come together, they stick together, and they go into fine mode. From the fine mode particles, some of them grow in size due to humidity, they absorb moisture from the atmosphere, they grow, and then they come to accumulation mode. Likewise, from the coarse mode, particles will collide and then they go into accumulation mode. So all these four modes exist simultaneously in the atmosphere. Now, in order to measure the properties of any of the modes, one of the most important properties is the number concentration, which is on the y-axis. So how many number of particles are there in the atmosphere in general in a given volume, let us say per centimeter cube or per meter cube. So one of the most popular instrument for that is a particle counter, either the CPC or OPC, optical particle counter or condensation particle counter. Uh, the core measurement technique in both is optical in nature. So what is happening here is you have a sampling inlet. Aerosols are entering through the sampling inlet, and they are of different size. Keep that in mind. They go in this central chamber. You have a laser here and you have a detector here, photo detector, right? Now, the laser has a specific wavelength. Let us say it has a wavelength of 550 nanometer. As you all know, if the particle size is very, very small, it will simply miss the laser. Likewise, if the particle is very big, the scattering intensity will be enormous. Now, the detector, the photodetectors are sensitive enough. However, if the particle is very small or the scattering signal is very weak, your photodetector might not detect it. Uh, and if the particle is very large, the scattering intensity will be so high that the photodetector will be saturated. So these are the challenges in this domain. So in order to overcome some of these, what we do is in the sampling inlet, all size of particles are coming. Then we have a porous membrane surrounding this central tube. And this porous membrane is filled with a specific liquid, usually butanol, and in more advanced instruments, we have deionized water is there. So the liquid permeates through the wall of this tube. So these tubes are made up of a specific membrane. So usually there are specific materials like Gore-Tex is there, or so Gore-Tex is also used in sportswear. The inner lining of the sportswear is a thin membrane called Gore-Tex. So why it is required for humans is because those who do sports, extreme sports, let us say in cold condition, uh, you are sweating from inside, right? So the sweat need to go out of the body, and due to body heat, it will convert into vapor, and this membrane will allow that vapor to go out. Let us say it is raining outside and you don't want to get wet. So this membrane will also block the liquid water from coming in. It means it is blocking the liquid water to go across the membrane, but at the same time, it is allowing the vapor to cross the membrane. So the butanol vapor or the water vapor will cross this membrane and will mix with the flow. And when that happens, these particles will absorb that moisture or the butanol and they will grow in size. So you can see these very, very tiny particles, and as they move forward, they have grown. Why we need to do that? So that the laser, all these particles are visible to the laser, and the scattering signal is sufficient enough so that the detector can detect that, right? So what is happening is the laser is firing continuously and the detector is continuously detecting something. Now, whenever a particle is crossing the laser beam, it will interrupt the continuity on the detector. So the detector will detect a dip in the light intensity. Every single dip is recorded as a single particle. Now, if I change the position of the detector from directly facing the laser to somewhere perpendicular to the laser, then the detector is not detecting any signal. However, whenever the particle is crossing the laser beam, the laser will hit the particle will scatter radiation, and some part of radiation will reach the detector. So that's how we count the particles one by one, and depending on how much volume of air the instrument has taken in and how much particles it has counted per unit time, we can calculate the number concentration of these particles, and we can get the total number of particles per unit volume in the atmosphere. So this is one of the most popular instruments for measuring number concentration. Optical equivalents are also available. The second one is for the mass. So this is one of the very popular instrument called the tapered element oscillating microbalance. So you can see an aerosol particle is, excuse me, an aerosol particle is entering, it is going through the inlet. Uh, Here, what is happening, this is substrate, electronic substrate is there, and potential is applied onto this substrate, a potential difference. So because of that potential difference, this substrate is vibrating at a given frequency, and that frequency is measured by this amplifier frequency counter. Now, once I deposit some particle on this substrate, due to the mass of the particle, the oscillation frequency of this substrate will change. So any such change in the oscillation frequency will be detected by this amplifier and frequency counter. And using specific calibration values, we can convert into the mass concentration of the particle. So this is one of the very popular online instrument for real-time mass concentration of particles. Now, you can see on the top this inlet PM10 or TSP, total suspended particulate, or PM2.5. So if I change this inlet to PM10, I get the PM10 mass. If I replace it with a PM2.5 head, I get only PM2.5 mass. If I change it to a whole air inlet, then I get total suspended particulate mass. So the same instrument, but using different cutoff or different sampling inlets, I can get different, mass category, PM1 or PM2.5 or PM10 or TSP, the total suspended particulate. Now, coming to size distribution, for size distribution, as I mentioned earlier, the size of aerosols, they span several orders of magnitude. And it is not possible for a single instrument to measure the entire size spectra from roughly 1 or 3 nanometers to roughly hundreds of thousands of nanometers. So for that, what we do, we have different techniques to measure. So for larger particles which are sensitive to light, which have the potential to scatter light, visible radiation, we use optical techniques. And for the smaller particles which you know are not sensitive to optical radiation, we use different techniques. Electrical mobility, I will talk about that in the next slide. So talking about this instrument where we use optical technique to count the particle and also to ascertain their size. What is the size of these particles? You have the inlet, so particles are coming through this, and using aerodynamic lensing, this is a specific kind of structure of the instrument as well as the uh, flow regime that we select particles one by one. So single particle is entering this optical chamber. So in this flow, there can be thousands of particles, but when they enter the optical chamber, they usually enter one by one. So that much of dilution we are doing in this chamber. And we fix the dilution ratio. So 1 is to 100 or 1 is to 1000 or 1 is to 10,000 and likewise. So it means one portion of ambient air and 10,000 portion of clean air. So why we need to do that? So that this optical chamber is, the optical chamber here is not contaminated. That's one thing. And second, only one particle crosses the laser stream at a time. So what you see here is there are two laser streams, one on the top and one on the top here, one at the bottom here. And there is a gap between two lasers and there is a photo detector, okay? So when a particle crosses the first laser beam, the detector will detect a signal blip here. And then when it will cross the second laser beam, again a blip will be detected, and the time between these two, what we call time of flight, elapsed time, determines the size of the particle, because the size of the particle depends on the flow as well. The flow is fixed irrespective of what is the size of the particle. Larger particles will have more inertia, smaller particles will have lesser inertia, smaller particles will move faster, larger particles will move slower, right? So based on that, we can size the particles and as well as count how many particles are growing, are crossing the laser. So this is something what you get on the instrument screen. You can see a size distribution. So it is very much like this. On the X, you have the size, let us say from 1000 nanometer to 10,000 nanometer. And on the Y-axis, you have particle number concentration. So for each size, so this instrument has roughly 36 or 40 bins between 1000 and 10,000. So there are 40 bins. It means in 40 sizes, I get the number of particles. So I get a distribution of number concentration, so aerosol size distribution. So this is one technique which is primarily used for larger particles which are sensitive to optical scattering. Then there is another technique which uses the electrical mobility and inertia of the particles. And this instrument is called SMPS, Scanning Mobility Particle Sizer. So what we do here is charged aerosol flow goes in polydisperse. Polydisperse means literally what you see on the screen here, the multimodal aerosol distribution, which is actually the kind of aerosols in the atmosphere. We don't have a fixed size of aerosols in the atmosphere, means we don't have just 1 micrometer size of aerosols or 100 nanometer size. No, we have an entire size range of aerosols existing simultaneously in the atmosphere. So all these four modes are present. So polydisperse. Now we want to count how many particles are there in each of these sizes. Let us say between 3 to 5 nanometers, between 5 to 10 nanometers, between 10 to 15 nanometers, and so on, right? How do we do that? How many number of particles in each size bin? For that, what we do is there's a central electrode which is having a very high voltage. When I say high voltage, it can be anywhere between 10,000 to 40,000 volts. Probably not 40, I think between 10,000 to 25,000 volts or something. And it is scanning. So the voltage is scanning between 10,000 to 25,000 in a cyclic manner. So it will go slowly up from 10 to 25,000 and then it will come back to 10. Then again, it will scan up. So what will happen? These particles, aerosols, they they go through a specific instrument called the aerosol charger, and they get different charges. So positive +3, +2, +1 charge, -1, -2, and so on. now that they are charged particles, when they enter, there is a very, very strong electric field because the outer section is grounded. And because of this electric field, and since these particles are charged, they experience a force in the field, right? Electrostatic force. And because of that, depending on their mass to charge ratio, they get attracted towards the central rod, right? And you see there's a small cut here in the center, and then there's a small cut here at the end. So very, very heavy particles, depending on how much is the strength of the field, smaller particles will hit and then get lost in the center. Very, very large particles will get hit the wall or will get exhausted from here. Only the right size of particle will have its trajectory so that it ends right at the exit of the flow here, where we get the monodisperse aerosol flow. If I change the voltage here, I get a different size of monodisperse particles. So if I scan from 10,000 to 25,000, I start getting right from very, very small particles to very, very large particles, right? So right from roughly 3 or 8 nanometer size particles to roughly 100 to 400 nanometer size particles, I can scan and I can get their size distribution. Now, so this was about physical properties. How do we measure aerosol physical properties? Coming back to aerosol coming to aerosol optical properties, there are two very, very important instruments I wanted to highlight. One is the nephelometer, which measures the spectral scattering and backscattering coefficient of aerosols. So on the left, you see on the screen a schematic diagram of a nephelometer, where you have a light source here, the lamp. You have air sample inlet, so aerosols flow in, ambient air comes in through this, and then it traverses and goes out from here. Okay, then there's a lamp here, and there's a whole lot of optics here, what we call the photomultiplier tubes, and the acting as a detector, right? So what is happening in this sensing volume is all these particles are floating in the air here, right? And light is falling on the particles will scatter this light radiation in all the possible directions, right? Some of that light will travel in the forward direction and will through a very fine slit will reach the lens, and the lens will collimate it to different photomultiplier tubes, green, red, or blue, or different wavelengths, right? So this is what we call integrating nephelometer. So remember, when radiation or light is hitting a particle, it will scatter in all the directions. So all 360 degrees. So if a particle is here, this light will hit it, and the angle between them will be very, very small. If the particle is here, the light will hit, and the angle of scattering will be very large. So it will integrate right from this angle to this angle, roughly from 170 degree to, right from 7 degree to 170-degree integration of scattering. So that's why it is called integrating nephelometer, and it will give you the scattering coefficient of aerosols in different wavelengths, as well as the back scattering coefficient, how much it is scattering in the forward direction, how much the particle is scattering in the backward direction. Why that is important is also because you remember aerosols are in the atmosphere, and the primary source of radiation for us is the sun, right? So solar radiation is coming from the top, from different directions actually. When I say from the top, if the sun is at the zenith, then it is from the top. Otherwise, from morning till evening, the angle will change, right? And this radiation will fall on the aerosols. Depending on their backscatter fraction, some of that radiation will be reflected back to space directly. So aerosols play a very vital role, as I mentioned earlier, in cooling down the atmosphere. So how much they scatter back, that depends on their backscatter fraction, and this instrument can measure that property. Okay. Then we have the spectral absorption coefficient. We have the atherometer, which measures the spectral absorption, and through that we can calculate the black carbon concentration, which is a physical property or a chemical mass, as well as chemical property, black carbon. So there's a filter tape inside this instrument, and what is happening is the filter tape is moving slowly, and the light is impinging on the filter. So think of, there's a very clean filter, this one, and there is a filter on which a lot of aerosols are deposited already, right? And this is my reference I naught, so unloaded filter. This is my reference I1 and this is my reference I2. So intensity of light, original intensity of light is I naught. After passing through one of the filters where some loading is there, some deposition is there, the intensity drops down to I2. So if I take the logarithmic ratio of that, I get attenuation of light through the filter. And using calibration values, I can calculate the amount of absorption because of this attenuation, right? So absorption is related to attenuation by means of the volume of air which has passed and the amount of attenuation and the time. So, and then there is a specific number called the mass absorption efficiency. When we multiply that mass absorption efficiency with the absorption coefficient, we get the black carbon concentration. Okay. In the chemical properties, one of the most important instruments is the HRTOF AMS, high resolution time of flight mass spectrometer. So this is an online instrument which can give us real-time chemical composition of aerosol particles. As you can see, I mean, it's a massive, bulky, and really complex instrument. So you have a sampling inlet here. So aerosols will flow in through this inlet. Then there is aerodynamic lensing. So in order to ensure that only one particle is crossing this chamber at a time, the particles are subsequently removed one by one in this entire ADL aerodynamic lensing passage. So once they move into this chamber, the concentration is further reduced through very high efficiency vacuum pumps. And finally, after this chamber, we ensure that one particle is entering the finally time of flight mass spectrometer chamber. As the particle goes in, uh, it gains velocity because of very high suction, very high vacuum, and it hits a very hot plate uh, where non-refractory particles means particles which vaporizes at less than roughly 600 degrees C, they get vaporized, they get fragmented and vaporized. Now, there are, once these are vaporized, the vapors will move on to a different chamber, and there we have a specific sensors which detect the mass to charge ratio of these different vapors, and then using calibration libraries we calculate the specific chemical composition of aerosols. So when I talk about online chemical composition, in real time, this instrument can give you how much of organic fraction is there in the aerosol, how much of nitrate is there, how much of sulfate is there, sulfate nitrate organic fraction, and how much of ammonia is there. So 4 to 5 bulk aerosol properties can be found using this instrument. Then in addition to this, you have offline techniques, which I'm not talking about here, but in the offline techniques, what you have primarily is, let me actually go back to the offline technique slide, and then probably I can comment something on that. So you have offline physical properties. So you have a blank filter, you weigh the filter beforehand, then you put it in the instrument. The instrument will suction the ambient air, and depending on the porosity of the filter, different size of particles will be deposited on the filter, right? And after 24 hours, you take the filter out, you dry the filter, and then weigh it again. And the difference of mass will tell you the amount of particles which are deposited on the filter. And once you divide it with the volume of air which has crossed the filter in 24 hours, you get the mass concentration of these particles. So that is one very simple technique which we use to measure the aerosol mass offline. Then you have the chemical analysis. So again, you have the filters, and then you take punches on these filter, different segments of the filter from different areas, and then you do offline chemical analysis in the lab, and there are multitude of chemical analysis techniques are there. You dissolve the filter. Some filters can be dissolved, some filter need to be burned and then dissolved into specific chemicals. Some can be dissolved in water, and so on, so on. So depending on which sort of a species you are looking, refractory, non-refractory, carbon base, and so on, or metal analysis you wish to do, there are different set of offline techniques one need to follow. So with this, I hope I have given a broad overview of what are the physical, optical, and chemical properties of aerosols. How do we measure both in situ as well as using remote sensing techniques? And then in situ, we have offline, and then offline technique as well as online techniques. Then I primarily focused here on online in situ techniques. Um then there are ground-based remote sensing measurements as well. There are, PRL has established a LiDAR network across India, as well as established uh, aerosol measurement network called the RFINet, and so on. So all these are ground-based remote sensing measurements are there, using which we can measure different aerosol properties. Okay, so I will probably stop here. I know there is a lot of ground to cover. There is much more one can talk about, but in the interest of time, I'll stop and I will be happy to take questions.
All right. Thank you so much, Dr. Aditya. It was a very well structured and very clearly, clear in intent. I hope the participants have been benefited a lot. I'll put some few questions to you, which we are receiving online from the participants.
Okay.
Like Saikat is asking, what is the fundamental difference in the atmospheric residence time between PM 2.5 and PM 10?
Okay. So let me very quickly go back. So PM 2.5, as you know, are, hold on, sorry. PM 2.5 are particles which are roughly of this size, and lower. So this is 1 micrometer. So 2.5 will be somewhere here. And PM10 is all the particles of 10 micrometer or less, right? Now PM10 particles, since they are larger in size, they have more mass, they are more prone to sedimentation losses. Okay, I think I had a slide on this, right? So sedimentation losses are the primary factors. They are under the influence of gravity, so they will settle down very rapidly. PM
Yeah.
2.5 particles have larger lifetime because they don't, they don't get influenced so much by coagulation or diffusion losses, and sedimentation losses are very less in that regime. So the lifetime of PM 2.5 particles in the atmosphere is roughly 4 to 5 days, whereas PM10 will be few hours only.
Yeah. So another question Anushka is asking, can micro sensors or low cost ground units ever replace high precision sun photometers? Okay.
Okay, that's a wonderful question. So that is also one of my area of research, and in the interest of time, I have not included that part, the lightweight low cost sensor part. Um Now, in terms of precision, they cannot replace the high grade research, instruments. However, in terms of you say, replicating those measurements to a reasonable accuracy, they are pretty good. I mean, I will give you a simple example. uh, if I have a very high precision high-end thermometer which can give me the temperature of this room to 4 or 5 decimals, I mean, that is wonderful, but probably I don't need it for my day-to-day applications. What I want is, what is the temperature of this room? Is it between 24 to 26 degrees? If I get that information, I think I will be happy. For some specific processes, I might need to control the temperature to probably third order of decimal, 24.343 degrees, right? Then I definitely need very, very high precision thermometer. So likewise, depending on specific applications, we can, decide whether we need to go for research grade or we need to go for lightweight low cost sensor.
Yeah.
If I have a distributed network of low cost sensors, probably I can talk much about, atmospheric aerosols and their properties. For example, if I have just one very high grade sensor, high resolution research grade sensor measuring properties out there versus I have 10 low cost sensors spread across the city, then I will be much more confident talking about the aerosol properties of the city rather than based on just one single measurement. So again, there are different aspects to look into.
Yeah, right. One last question we can take up. Does aerosol coagulation significantly accelerate in highly polluted air? And then connected one, if so, do models need real-time relative humidity inputs to capture how fast these swelling particles collide?
Okay. Um, I'm afraid I don't have, the best answer or the correct answer. They do coagulate, no doubt, but whether they coagulate faster in urban or highly polluted environment, I'm not very sure. Only thing I can say is probably that in highly polluted environments, you have more of VOCs, volatile organic compounds. You have more vapors in the atmosphere. These vapors can condense. Uh, Aerosols can get aged very rapidly in the urban atmosphere, highly polluted atmosphere. They will coagulate naturally, no doubt. Depending on the humidity regime, definitely they will grow. Of course, it also depends on the composition. So, in a nutshell, a straightforward answer is yes, they will definitely coagulate faster. They will grow faster, probably in urban environment because they get aged very fast, and aged aerosols will absorb more moisture rapidly as compared to fresh aerosols or fresh emissions. Now, do models need to take care of these processes? I think very much yes. However, the exact rate reactions, the exact chemical processes or aging need to be understood in greater detail. There are different groups in India as well as abroad who are working on updating the entire chemical reactions in models like WRF chem and so on. And many of them have definitely got huge success, and they have demonstrated that by updating some of these features in the models are able to replicate the real world scenario much more closely and much more realistically.
Yeah, so with this, Dr. Aditya, I thank you on behalf of entire IIRS team for the enriching session that you have delivered today. We greatly appreciate your thorough introduction to aerosol characteristics and the various instruments used to measure them. Your detailed explanations on the core working principles have made these complex optical, physical, and chemical measurement technologies much easier to understand to our audience. I thank you so much once again for your time and effort
Yeah,
and
thanks very
sharing
much
your
for this
knowledge with us
opportunity.
today.
Yeah,
Thank you
thank
so
you.
much. Thank
Thanks
you.
very much. Bye.
So the next session starts at 1:45. Kindly please stay tuned till then. We'll meet you back at 1:45 p.m. Thank you.
Yes, sir, very much. Yeah.
So, very good afternoon to everyone present.
Yeah, you can put it to full screen mode, Dr. Oja. So, welcome back. It is my pleasure to introduce Dr. Narendra Oja from Physical Research Laboratory, Ahmedabad, PRL. Dr. Oja is a distinguished atmospheric scientist specializing in atmospheric chemistry, air quality monitoring, trace gases, aerosol climate interactions, and chemistry transport modeling. His recent research is also in the area of machine learning applications. His research integrates observations and advanced numerical models to understand atmospheric composition and its implications for climate and environmental change. I once again welcome you, Dr. Oja, for this session today. Over to you.
Thank you very much, Manu. Thank you for inviting me to this activity. And as you said, my main interest is using computational resources to do the simulations. And we have been doing process-based calculations for quite some time. And we have also now using emerging techniques like artificial intelligence, machine learning, and deep learning. And today I will discuss mainly that aspects which are related to the modeling for aerosol parameters. So, first we will briefly discuss how different processes are affecting aerosols. I will not cover the scientific part in detail because I saw that many courses already have talked about. Just to summarize what is concerned for modeling is that aerosols are not always emitted directly. Many aerosols like nitrate, sulfate, secondary organic aerosols, they form through different type of gas phase emissions and followed by chemistry. Some aerosols, of course, like black carbon, etc., they are coming as a directly from the emission source like biomass burning. And getting this type of fields, especially like PM 2.5, that is some of sulfate, nitrate, and some other fine small size aerosols. So getting their fields for entire region, that is very critical because aerosols have large impact on human health. So, but of course, we do not have measurements at every place. So, and there is such a diversity in these type of different sources, and chemistry is also involved, and transport is more governed by winds and meteorological conditions. So, quite a bit complex set of processes control how the end, in the end, how aerosols will be distributed, what will be their levels at a given study region. So that's why the modeling is very much required because we have to understand which sources are contributing more. And in the end, we want to have some estimation for entire country or South Asia region. So you can see the entire global distribution that is coming from some global reanalysis type of products. So you can see that compared to May, that is northern hemisphere summer. If you see winter time, you can see clearly these pollution hotspots, the Gangetic Plain and this African region. You can see East China. So these are some regions which are having hotspots of high aerosols near surface. And Lelywild used some models to understand that how more aerosols can affect the air quality of South Asia, and they found that more health impacts are in the Asian region due to aerosols. And this process, you can see sulfate, ammonium, organic carbon, black carbon. So although they can be high near the surface, but they can also get distributed because you know that Asia has a strong monsoon system. So aerosols may not be only stick to the near sources. They can be uplifted once aerosols get transported above clouds. They can also affect large regions. So like SO2 emissions, once they convert to sulfate aerosols, they can be distributed over larger regions. So if you remove emissions from South Asia, then this you can see the effect which was happening all over that is now gone. So this tells us that besides the emissions, large scale dynamics is also critical for aerosol fields. So with this background, we understand that modeling is simulations is very important. Of course, we don't have observations everywhere. So, but everyone wants to know how is the aerosol loading around them, so they can do the computation. So then we need to understand sources, because as we saw that aerosols can be emitted, they can be formed chemically, or they can be transported from somewhere else. So to understand the processes, sources, to also understand what if scenario, like I removed some emissions from India to see how it is changing the aerosol distribution over South Asia. So that is called what if scenario. They are useful for designing new policies, that okay, if we reduce 20% emission, how much benefit we can get, or suppose 20% emission are to be increased, so how it will affect the air quality. Similarly, forecasting is also now becoming very important. We need to know in advance how the, like weather forecasting we are all the time using. We need to know how weather will be on the next 2 days. So they are coining a new word called chemical weather. How will be the aerosol atmospheric composition next few days? In particular, what will be levels of ozone and particulate matter? So that is called forecasting. And then, as I said, to inform policies, like what could be the best way to mitigate pollution and climate change. So far you have understood about how satellites give you idea about aerosols. People launch balloons to take samples. They also put instrument on aircraft. Lasers are very popular tools. They can tell us where attenuation is more, so vertical profiles of aerosols. But another component is modeling. Suppose we have this type of measurements. So how we build computational models, how we test that, okay, this is a good model for our region. So that all is supported by powerful computers. This is photo of Param Vikram. It is named in the honor of Vikram Sarabhai. So this is our supercomputing facility. So such machines are required to calculate, either you want to simulate entire globe, or you want to look at a particular region but at high resolution. So you can imagine, if you are trying to calculate entire globe, then you have coarse resolution. You can calculate every 100 kilometers. But if you are focusing on a particular region like Africa, India, calculations are done at very high resolution. So they are also computationally very demanding. So the philosophy behind modeling is that we have to start with the understanding of the physical and chemical processes. But based on that, we have some conceptual model, like we understand that from where aerosols are coming. They are coming from anthropogenic emissions. They are coming from forest fires. They are coming from chemistry. So all those processes are written in form of complex models. But in actual modeling, only knowing philosophically is not enough. We need to arrive at some mathematical treatment that, okay, for wildfires are there, but how much they translate into emissions in form of maybe tons or kilograms per hour, whatever. Similarly, how much anthropogenic emissions are happening. So all the sources and all the things, they all have to be written mathematically so that we can sum and we can reduce these things. So what happens that in the end, whatever model is built or tested, whatever model is being prepared, in the end, it has to survive the comparison with experiments. If our model simulations in the end do not match with the experimental values of atmospheric fields, then we have to, so like this is snake and ladder, many of you would have played. So if initially you are at seeing some issues, you can keep on fixing, but in the end you compare with experiments, and if that doesn't match well, you may need to go back completely to look at, start even from what was physical process. Did we miss some important source? Did we miss some important thing? Is our transport is not proper? So that type of, we have to go completely back and improve the model. So basically these models are adding all the sources, like how much is emitted, and it is simply shown as emission E, but it has three terms like direct emissions from biomass burning, anthropogenic emissions, various sources. Similarly, chemical production. So you know that at least half of the aerosols that is in the urban regions, that can be secondary formed through chemistry of sulfur dioxide to sulfate, ammonia, this nitrogen oxides to nitrate. So that all is going into the chemical production. Similarly, there can be loss processes, and through wind and dynamics, some extra pollution enters whichever region you want to calculate, something will enter and some pollution from your region through winds will also be flowing out. So all these has to be considered. So a quick list is that we have to have idea on emission inventories, like what is the anthropogenic emission. So each component is basically developed and by different groups they are maintaining. For example, anthropogenic emissions, they are developed by EDGAR and some ECMWF scans. In Asia, REEF is a good inventory. So they try to look at the activity data, like how much fossil fuel is burnt, and based on chamber experiment, they try to estimate like if this much amount is burnt, what will be the corresponding kilograms of a particular gas or aerosol. Similarly, biomass burning. The satellites are very powerful tools to detect fire because they can sense the temperature at a given point. So groups like NCAR in US, they develop this fire inventory, FIN. So that is very much used into modeling. Similarly, natural emissions of organic compounds, they are also very important, but they depend on meteorological conditions. So plants, depending upon vegetation, what type of plants are there and what type of atmospheric conditions are there. Normally when temperature is high, then natural emissions can go up. So these organic compounds then go chemical and other transformations. In the end, they can also become aerosols. In the removal, dry and wet deposition is very common. Anytime when in some polluted environment, whenever some lot of rain happens, if you come out of your place, then you see that visibility is really better. So that is because of the wet removal of the aerosols. Because of the rainfall, it is removing a lot of the aerosols. Dry deposition is also there because of gravity. If aerosol size become bigger, because of gravity, they can fall and remove from the atmosphere. And as I said, transport and dynamics is important. Through winds, the aerosols can get into our region or they can be flown out. Chemical mechanism is very important. Chemical mechanism basically is a set of chemical reactions between different chemical species that tells like how the chemical transformation will happening. So normally in atmosphere, the chemistry is highly complex. Roughly 4,000 to 5,000 different chemical reactions are there in the atmosphere. But if we want to add all the details in the models will be extremely slow. It will be very difficult to run them. So models, especially the three-dimensional climate type models, they use very simple treatment of chemistry. So those chemical mechanisms are quite simple in the three-dimensional climate models. So now when you know all the key sources, like how dust is generated. So dust is generated when winds are very strong and the surface is erodible. So depending upon the land surface properties and depending upon wind, dust emissions take place. So you can see that so many different factors are contributing to the aerosol loading. And everything is somehow estimated, like inventory, how you calculate, fire, how you detect their contribution, natural emissions, how you parameterize, how you calculate how much dust should be emitted. Similarly, various removal process. So each of this calculation will have some or other uncertainty. Some believe that for regions like South Asia, anthropogenic emissions are highly uncertain. But if you look at each process, so every process is contributing various uncertainties into the model. So you can know that whenever you take a model output and you deploy a machine and try to match, they never match. So if you have to imagine how I improve the model, so as I said earlier, giving example of this snake and ladder, so each and every process has to be looked into it. So I will show some results. This WARChem has been very popular model for India. So we are covering this entire South Asia region. And we are using simulation at every 27 kilometer by 27 kilometer. So compared to the global models, that is quite good resolution. So before we look at the aerosols, we can also look how is the meteorological conditions, because that is controlling a lot of processes related to aerosols. So you can see December and May, That is two very contrasting atmospheric seasons. December is mostly our winter in this hemisphere. May is our typical summer conditions. You know that temperature is very, very high. So you can see that compared to this Indian meteorological reanalysis, you can see that our model is also getting it quite right. Similarly, humidity is less during May. And you can see during December also, you can see the agreement between WRF model, that is our chemistry climate model. It is quite good with the IMD. So meteorological features and even dynamics, you can see that winds, the way they are in IMD reanalysis, they look similar in the model. So what we can say that atmospheric conditions and seasonal change, they are proper in the model. So we can use this model to calculate suppose aerosols. So this lower panel is for the aerosol data. You can see that compared to global models, they were quite underestimating aerosol loading. But we are, because of including all our regional emission inventories and very good representation of meteorological conditions, we can better capture the aerosols during December. You know this entire Gangetic Plain, high aerosol feature. During May, this is lower. So aerosol processes are slightly different than the gas phase processes. Normally, if you look at ozone, so that is high during summer. But aerosols, because of deeper boundary layer during summer, the pollution gets more diluted. So that feature you can see when you compare this winter value with the summer value. It is very important to look at, because PM2.5 is a diagnostic term. It is basically sum of your sulfate, nitrate, black carbon, ammonium. So if our bulk aerosol is right also, still to understand the processes, we have to look at individual components. So you can see for summer conditions, this is our model calculations, and these are the observations from various groups like from PRL and IITM. And this data is coming for oceanic region. The observations are conducted by CSIR, National Institute of Oceanography. So what you can see is that normally sulfate contribution is getting captured by this, but somehow there is a lot of difference in nitrate and also the black carbon. So you can see that sometimes black carbon is overestimated by the model. So what happens that if some of these parameters, the composition of aerosols, that is overestimated, so their impact on climate will also be not proper. If you look at the Indian Ocean region, so observations are showing much more variability, like about 20 microgram. But our models, they are underestimating the variations in the Indian Ocean. So we find that although we are including all the processes and emission inventories and good meteorology for India, so although we are getting better data sets compared to global models, but still there are a lot of differences. So a lot of more process understanding has to be improved. This is a application on this well-known problem on the high aerosol loading in the Gangetic Plain, that every post-monsoon, that is November, every post-monsoon happens. So it is believed that a lot of effect is coming from the crop residue burning in Punjab, Haryana regions. So what we try to do, we first included all the emission inventory, then we simply removed the fire inventory from the calculation and calculated the change that is being caused. So we can see that this Punjab Haryana fires, they are affecting northwest of the Gangetic Plain. In November, because of dynamics, that is distributed more. But December, when Gangetic Plain has maximum pollution, if you see December, when it is very widespread pollution is there, then in this region, you don't see much effect of the fire. So that is telling the effect of boundary layer height. You can see boundary layer was 400, 500 meter in October, but towards winter, it has become less than 200 meters. So because of such shallow boundary layer, such cold conditions of the Gangetic Plain, the wildfires are not there, but still pollution in this region is not enhanced. Fires are contributing mostly to the Himalayan foothill regions that you can see. So using this type of chemistry climate models, we can understand the role of meteorology, atmospheric dynamics as compared to the emissions coming from fires. This again, we see the contribution of different sources like anthropogenic emissions. So you can see that December and a lot of effects are coming from anthropogenic sources. Fires are also contributing. You can see during May, in May month, there is a lot of wildfires in the Himalayan region that is also contributing. Interestingly, natural processes like biogenic emissions, they add a lot of organic compounds and they are contributing to the aerosol formation. So there are a lot of different processes that we are trying to calculate from the models. And these emissions, they are not confined to the only continental region. And you can also see that effect from Southeast Asia that is also entering the Indian Ocean. So this type of models are very good to understand the contribution of emissions and the dynamics. Then what we are trying to calculate is how these aerosols are affecting the radiation. So if you look at the role of aerosols, so aerosols are kind of reducing the radiation that is arriving at the Earth's surface because they are attenuating the incoming solar radiation. And that is also reducing the height of PBLH, that is boundary layer. So earlier also we saw that when cold conditions are there, aerosol buildup increases. And because of that, you may know that Gangetic Plain observes a lot of cold and foggy conditions. So this is the aerosol radiation feedback that is again affecting the meteorology. And because this meteorology is disturbed by aerosols, so they give a feedback and increase slightly the aerosols. So because of this feedback mechanism, once aerosols are high at Gangetic Plain, they are reducing the temperature and boundary layer, and they are giving this type of feedback. So models are now really very complex, and they can help us understand these processes. Now, next, I will try to take you to a different type of approach that is kind of machine learning. So as we can see that from process-based models, although we are getting a lot of information, but there is a lot of scatter if you compare with observations versus models. So our process models, although they are getting good amount of features, they are still having a lot of issues. And issues are more in the Himalayan foothills because of the highly complex terrain and these mountain valley systems. They kind of trap the atmospheric pollutants, but through boundary layer dynamics and because of some local process and because of terrain, the wind systems are also slightly different, what you call as a mountain valley wind system. So those type of dynamics is normally not captured by the conventional climate models. The reason is that topography changes very fast in the Himalaya. So if at a 10 kilometer, even 10 kilometer resolution, the high altitude mountains, their height is underestimated. So because this terrain that affects the local wind systems, those features don't show up into the model's dynamics. So if our dynamics is not right in the model, they fail to get the pollutants and aerosol distribution right. So we thought to test use of AI because AI is more data oriented. So even if the process is not properly presented into the physics or chemistry based model, but suppose we collect some measurements, so can then we make a better model? So we collected data of PM2.5, aerosol size distribution, and several other parameters from Doon Valley, that is where this IIRS is located. So in that same region, we have collected some measurements, and we also used several satellite-based products for many years. So what we see that various global model data, they are quite good in capturing temperature, humidity, but chemical parameters show a lot of scatter. So probably we need to use some AI methods to make better models. So how we are trying to do it, you can focus on this PM2.5 models. So we have included temperature, humidity, precipitation, boundary layer height, wind speed, wind direction. These type of different parameters we have included in the machine learning model. And then we are trying to simulate the observations. So we can see that in Doon Valley, we are getting R equal to 0.6 or even 0.7. So that type of performance is very superior to our traditional global models, even the reanalysis data. So this is quite a good success that we are getting. So the idea is that if process-based models are not giving us very good aerosol variability at a region, but suppose we can make measurements at that place for some time. So we can kind of use that data to build AI ML models, which can give us better prediction in the when we do not have measurements, we can use the AI/ML model instead of the conventional model. So how this improves our understanding? You can see that various models are available. There you can see this is the PM2.5. So their performance was R values are very low. But when we enhance the models using AI/ML and observations, you can see the correlation is increasing very much. And at the same time, errors are going very much down. So this is suggesting that AI/ML can help us to produce reliable model fields. And when we suppose this is some period when we do not have measurements, so this you can focus on PM2.5 experience. So if sometimes our measurements are not operating, some instrument is broken, but we can use our machine learning code. So then we can see some extra days where observation was not there, but pollution level was high. So we can better constrain the impact of air pollution on public health. So the issues that gap of observations that can be addressed to some way by combining the AI/ML models. But this is only for one station in Dehradun. But now we want to generalize it for entire South Asia. So what we are trying to do is we are taking various available data sets from meteorology and chemical parameters. So as such, these chemical parameters are not in very good agreement with observations in India. But once you know the already what is the output field, so machine learning models can build a function between these inputs and apply that type of correction. So what we are doing is we are taking observations from several stations in India and correcting the reanalysis field first using machine learning. And then we are building a machine learning model that can give us this bias corrected fields of PM2.5. So you can see that we have tested many different configurations, and using IMD meteorological reanalysis and CAMS chemistry, we are getting a quite good model for calculating the aerosol distribution near surface across Indian region. So in the end, we want to build a proper regional level atmospheric model where where we can kind of use. So normally the conventional models, they work like this. You provide a global field at coarse resolution that goes as an initial and boundary condition for the regional model. Then you provide all the regional information, and then you can generate high resolution model simulation. This is our conventional flow of regional modeling. But what we are trying using AI, we are giving this deep learning framework the input global field as an one parameter and the output of our large-scale simulation as a training data set. So by knowing the both input as well as the output, this DL emulator is getting trained. So once our deep learning framework is getting trained, so then we can use this emulator to calculate the aerosol field, meteorological field, which will be effectively what you would have gone from a process-based large-scale simulation. Because large-scale simulation requires much more computational effort. Deep learning models also need more computational resources, particularly during the training process. And they need large amount of data for training. But once that all is done, and then once this DL emulator is built and evaluated, then this can be a really portable model that many students and people in academics, and they can use this type of emulators. It can run even your laptop with quite good speed, which is not possible to run this type of models. So this is our future direction, like how we can use deep learning to build kind of a full-fledged regional scale atmospheric model. So this is, we have tested many different configurations for regional modeling, starting from, so they are based on convolutional neural networks and different type of architectures we have tested. So you can see that temperature fields are coming proper. Humidity is also getting proper by deep learning model. Ozone is also coming very good. However, in PM2.5, we are still seeing a lot of scope of improvement. This was our reference field, but our deep learning models, they are overestimating and over smoothing the variations that are seen here. So several variations are not getting captured, plus they are overestimating. So this is not a finalized thing yet. We are still developing, and we will be developing more versions of the deep learning emulators for aerosol modeling in the future. But As of now, this is already a significant step, which shows that there can be some emulators through which we can do fast computations of regional atmospheric distribution. So I would like to summarize what all I said. So first point is that by adding the emissions and performing the calculations related to chemistry, etc., aerosol distributions are being computed using for both regional scales and global scales. And they are using these process-based models. We are getting a lot of good insight in terms of role of different type of emissions, role of transport from Gangetic Plain to even Indian Ocean. But nevertheless, there are a lot of limitations. For example, model performances are quite limited in the Himalayan region. And then in the Indian Ocean also, the variabilities are not getting captured. Although the mean level of aerosol composition, sulfate nitrate, that is coming up, but the variations, they are not coming up. So it is possible. So one way is that we need to understand these processes more, and we can make these models more complex. We add more details into them. We refine the each emissions and the chemical treatments of the models. And another alternative approach that is emerging right now is based on AIML. Because so far the lack of observations, AIML could not be used heavily. But nowadays, observational data is becoming more and more available. Many groups in India are sharing their aerosol and gases measurements. So now the potential of AIML can be realized better. In addition, the satellite data sets, they are also coming at very high resolution in both space and time. So they are also entering as the inputs into the AIML model, because AIML does not go in terms of process. So even there is no causal relationship between an input and the target variable, still AIML, since it is a statistical approach, they can get benefit of that type of data. So it is possible to utilize more and more AIML models, AIML approaches, to basically produce more accurate data sets for atmospheric aerosols and meteorological parameters. So, so these are our future directions. So with that, I would like to conclude the presentation. And if there are any questions, I would like to take.
All right. Thanks a lot, Dr. Roger. It was indeed a very enlightening session on the modeling aspects of aerosols, which we had not covered yet. But with your session, I think that gap is also filled now. We can take a few questions. Yeah. So, one question is how do chemical transport models simulate complex aerosol cloud interactions?
Yes. So yeah, so these models have so most of these processes are actually parameterized. So parameterization is basically having some type of observational data from field campaigns and try to see how that process can be calculated one parameter can be derived in form of some other parameters. So most of the physical processes, they are being kind of parameterized in the model. So clouds are calculated. So cloud for calculation of clouds, first step is calculating convection. So convection is also parameterized. So there are dedicated schemes like Grell 3D scheme we have used for parameterizing convection. And then aerosol cloud processes, that is coming from the parameterization of microphysics and related processes. So these processes are kind of parameterized, and as such, they are containing a lot of uncertainty also. So when we have more data, especially from developing regions, then probably these parameterizations can be improved.
Right. So another question is models like WRF Chem, CMAQ, and GeoSChem all simulate air quality. What are the main factors that determine which model should we use for a specific study?
Yes, that is very good question. So what happens that there are different models. So first, as you yourself said, that GeoSChem also gives, but GeoSChem is a global model. So suppose you want to look at the global air quality. So you must be using a global model, even if it is not at such a resolution like our WATSChem simulations. But if your objective is to look at the global air quality, you have to go with that. But if your objective is to look at a given region like India, Africa, then it is better that you go with the regional model. And please note that these regional models are not totally independent of global models, because for long range transport, they still take the fields coming from the global model. So, um, so the information that global models generate, that also enters the regional model. But if you want to look at one particular region, you can go higher resolution and you can use a regional model.
Yeah. So another question is, what improvements are needed in boundary layer parameterizations to accurately simulate wintertime fog and aerosol accumulation over northern India?
Yes, that is again very important question. So the as you see right now, if you look at this model, so most of the boundary layer parameterization, like UNC University scheme is very popular, YSU, then MYJ scheme is very popular. So you note that these all schemes were developed from field data from other parts of India. They are not from Indian data sets. So what happens that they look at different meteorological parameters and try to derive boundary layer that they are looking in this field data. So field data of boundary layer variations, that has to be used for developing Indian parameterizations of boundary layer. So unfortunately, we do not have many PBL parameterizations from field data in India. So it seems that boundary layer height in India can go deeper into the summer, and it can be much shallower into the winter. So that feature is not coming properly. So by boundary layer and the errors in boundary layer, many studies in India show that because we don't get right boundary layer, that is why our PM 2.5 fields are quite biased. So sometimes people overcorrect the emissions, but as you said that boundary layer parameterization has to be corrected.
Hmm. Yeah. So last question we can take up. If satellites only pass over a region once or twice a day, how do models capture crop burning that happens during the hours when the satellite is not looking? Okay.
Yes, this is also a very good question and very relevant for today's time. So earlier the fire timing was slightly different, but right now the fire timing has changed. So satellites are missing many fires. So you are right. Once satellite has passed, if after that a fire is happening, then satellites miss it that time. Then next time when they are passing, maybe they look at some residual effect. But yes, so we need to have better monitoring of fires.
Yeah. So with this, I thank you, Ojaji, for delivering such an insightful session on aerosol modeling with a particular focus on the Indian context. I am sure our entire audience has been very well benefited from your talk. Thank you for your time and effort and delivering your session to our participants today. Thank you so much.
Thank you, Manu. And I am really happy to see so many important questions from the audience this time. So this is very nice. And I could not cover many technical details. So if any student need more clarification, they can just contact me through PRL email ID. I will be very happy. And this time I really appreciate the interaction with the students. Thank you, Manu.
Thank you. Thank you so much, Dr. Oja. Oh, so welcome back to the last technical session in this workshop. I am pleased to welcome Mr. Akhilesh Kumar from the University of New South Wales, Sydney. Mr. Kumar has worked extensively with satellite observations, atmospheric data sets, aerosol retrieval products, and geospatial data analysis. His expertise in handling Earth observation, reanalysis, and AeroNet data sets make him ideally suited to guide all of you participants through today's practical hands-on session involving aerosol data access, visualization, and analysis. I am thankful, Akhilesh, for you that you have joined us today to deliver this hands-on training session to all our connecting participants. Over to you.
Thank you, ma'am. And uh, thank you for the nice introduction as well. I hope this session is going to be useful for all of you. And I will start with the presentation. But before I do that, if you want to follow along with whatever I'm talking or showing here, you can scan this QR code and you'll get the code as well as the slides that is being used in this presentation. So good afternoon, everyone. I guess the previous sessions have talked with you about different aspects of aerosol optical depth, including the types of aerosols, the physics behind the retrievals, and so on. So in this session, we will look at some of the aerosol products that are already available and the ways to access and visualize them. So there are lots of AOD products available, some ground-based point measurement, but most are satellite derived. However, not all products are equally popular, so to say. So some are used more widely than the others. So in this session, we will look at two satellite, one reanalysis and one ground-based AOD product, and we will learn how to access and visualize them. This presentation is going to have two parts of it. So in the first part, we will look at the AOD products which are already available. And then in the second part, we will have a brief look at the IAOD software that Manu ma'am and I developed during my master's at IIRS. So let's have a look at Modi's DBDT product first, DBDT being dark, deep blue and dark target. So Modi's, as you would be aware, is a system of two satellites, Aqua and Terra. And AOD products are created using the satellite data from both this sensors using two sets of algorithms, deep blue or DB and dark target or DT. These two algorithms are designed to handle different sets of limitations with AOD retrieval, like a failure to retrieve AOD over bright surfaces, dependence on pre-computed library surface libraries, and so on. The things that are, I mean, we're not going to discuss in this presentation, obviously, but just to keep in mind that these are two different algorithms which are used to derive AOD from Modi's data. Moody's also provides a combined DBDT product, which can be accessed from NASA's LADS DAC portal. So NASA has different DAC portals, some for surface data, some for atmosphere data, and so on. So in previous years, what we used to do was we used to have a live demo of the retriever from the website itself. But you know, the website has a bit of latency. It takes some time to load, and we are pretty short on time. So what I would rather do this time is show you each step here, and then you can try it on your own. As I said earlier, you do have access to these slides and the codes that may be used here. So you can take your own time and follow along. So the first thing that we have to do is go to this website, the LADS website, and just a minute. And we can filter under the products tab as the aerosol products. And you will see a lot of aerosol data available. You need to scroll down a bit. And you should see these two names proper, the one with MOD at the beginning and the other with MYD. And these are basically the you know, the products which have been derived using either deep blue or deep or dark target or combined in general. So what we will do is we'll just select one that we want. For this presentation, I will go with which product? Yeah, I will go with the MYDO4 3K, which is the Moody's Aqua Aerosol 5-minute L2 swath 3 km data. So we'll select that, and then we'll click next to get to this time tab. And now we can select a range of dates here, or we can select multiple dates, like the individual dates, or we can also just go with a single date here. Once you have selected a date range, you can choose to download the data for a set of points, in which case you will get point data, or more commonly, we select a region, like I have done here using the custom box tool that you can see on the right hand side. Now, when you click next, what happens is it takes some time to do the search, based on the parameters that you have given, like the date and the product. And once it's completed, you have a set of images which are available for download. Now you can select the images that you need. You can select all the images if you want. And when you click next, then you go to the final step of this access process. Now you have to keep in mind that sometimes Moody's does, I mean, this tool, DAC tool, it does allow you to preview the images. If you go to the image tab there, but it doesn't always work. So don't worry if it doesn't work for you. That's totally fine. Anyways, you can always go to the last step, and here you will be given options for post processing. Now there are a lot of options available for you. I mean, if you do have a lot of scenes or tiles for the same date, you can mosaic them, you can combine them. You can also reproject the data into a desired coordinate system. But most importantly, you can request the data to be in a different file format. So for instance, you can get the files in a GeoTIFF format, which is way easier to work instead of say other formats like NetCDF, which is another very popular format for time series data. So once you have selected all the post processing parameters that you want, you can submit the request, and then you'll receive an email with instructions on how to download them. The email looks something like this. Now keep in mind that based on your request amount, so how many dates you have ordered, and like what's the size of your custom box, depending on that, this email may take anywhere from 10 minutes to even hours to arrive. So just hold your horses and give it some time. Don't have to worry, it will come eventually. So once you have the data, we can go with the visualization part. Uh, Now again, we have two ways to do the visualization. Uh, One is that you can use a GIS software like QGIS or ArcGIS or even Envy. I've seen example with QGIS here. Uh, or you can use a programming language like Python or R to visualize them. Here I have used Python to do the same. Once again, I would like to remind that the code is available on the GitHub repo that was accessible through the QR code that I provided at the beginning. So if you want the code, you can just get it from there. And that kind of, is everything that we need to know about accessing Moody's DBDT data from the NASA's LADS DAC platform. Now we will look at another, another Moody's data. And this product is derived using another algorithm called MAIAC. Now, this product is available on NASA's Earth Data Portal, but luckily for us, it's also available on Google Earth Engine, which is much easier to access using just few lines of code. Now, by default, Google Earth Engine uses JavaScript, but it's also possible to access it using Python, which is what I will show you next. So basically all you need is like this 5-6 lines of code here to access any data that is there on the Google Earth Engine platform. Now, one thing that you have to keep in mind, and which is the source of like the most common error, is that you need to have your Google Earth Engine account registered to be able to access any data on the portal. Now, in the GitHub repo, I have provided a link on how to do so. If you're getting an error like the account is not authenticated or something like that, like it is not the credentials are expired or it is not initialized, it generally means that your account is not registered. So just authenticate and configure your GE account, and this should work pretty easily. And while you can use this code to download the data, one thing to keep in mind is that we use Google Earth Engine to reduce data downloads and focus mostly on the analysis part of it. So it does not really make a lot of sense to download data from Google Earth Engine. Rather, what we generally do is we do the processing on the cloud and then we download the final product. Anyways, you can indeed, of course, download it. The code that I have provided does allow you to. Now, you can always also use the Google Earth Engine platform and the Python along with it to visualize the data. As you can see, we are just adding maybe 2 or 3 lines of extra code with that and maybe one extra module. Again, you can do this either using JavaScript in the Google Earth Engine code editor, or you can use Python pretty much everywhere else. And that's kind of it for the MODIS data for us. So the two examples that we saw here, the MODIS DBDT and the MAIIC product, these are basically satellite data products. Now, these products are pretty useful. However, they do come with certain limitations. And being a satellite data product, one of the primary limitations that they face is that they can have gaps in their coverage, particularly over bright surfaces or if there's a cloud and so on. They're also limited in their temporal resolution. While they're still better than normal reflectance products, like you get Landsat every 16 days, for instance, and Sentinel-2 every 5 days. So compared to that, of course, you are getting 1 or 2 scenes per day for a particular area, but still, it's pretty coarse, for a atmospheric monitoring point of view. Now, this is normally good enough, for most purposes, but the thing is, like, there isn't much we can do if we need images at more frequencies in certain circumstances, like say we have a dust storm and we want to monitor it. And lastly, we mainly get a total AOD thickness measurements from such data sets. And if we do want to get information about other parameters like the optical properties or different AOD types, we have to rely on post-processing. We don't get it in hand, so to say. So to overcome these limitations, we rely on something called as reanalysis products. Now, these are basically hybrid products that combine satellite measurements with model simulations. And what that means is that we get a continuous AOD product with absolutely no gaps in most circumstances. We also tend to have a better temporal resolution since we are not just relying on satellite measurements. We can like simulate some of the scenes where the data is not there. And most importantly, we can directly get AOD values for even the individual aerosol components like sea salt, dust, and others. Uh, but it sounds too good to be true, and of course, it's not all rainbows and sunshines here. Now, since the analysis data relies on physical models, it also tends to have biases, especially in situations where we don't have a lot of actual satellite data to work with. Now, we are going to have a look at one such reanalysis AOD data. It's called MERA2. Now, as is the case with most NASA data, there are multiple ways to access them. One of them is through their Earth data portal, and another is through the Google Earth engine, which I personally favor. And now we are going to have a look at both of these methods. Now, if we want to access MERA2 from the Earth data portal, we first need to get to this web link here. It's called disk GSFC links. And uh, I have highlighted a red portion there. It says MERA data are available here. So you have to click on that highlighted link, which opens up this portal, and it looks something like this. Now you just have to select on aerosols and you'll see a list of data sets that are available for access. Now, of course, we can't go through all of them here, and there are a lot. So there's also a technical documentation that is available. So please be sure to read through that to get an idea about all the other data sets that are available. For instance, if you can see in this screenshot here, oh no, you can't see it here, I guess. So there is one hourly data, then we have monthly mean data. Uh, so you can see, like, we have at least two kind of data sets available here. If I scroll down, there's also a 3 hour hourly data. So in this session, what we'll do is we'll just look at the ways to access the monthly data. Uh, now, but keep in mind that the step for accessing other data sets is almost same. There's no difference. So just for the steps that I show for the monthly data, and you can use this for even 3 hour or 1 hour data. Now, if you can see this, every data set has a code, so to say. So for monthly data, you have something called an XAER at the end. For the other data set, you have something like XADG. Now, all of these codes mean different data sets. Again, you will have to refer to the technical documentation to know what every data means. For now, we will just go with the monthly data. You'll also see a very small icon there. It's called subset or get data. Now, if you click on that, it will open up a new window, which looks like this. Now, here you can select a date range, as well as you can subset a smaller region if you want. Now, if you just select a date range, you will get the global data in the netcdf format. But if you are subsetting it, you can get it for a particular region, and you may also be able to change the output data format. I'm just going with the global data without any subsetting. So, and I've also selected a date range from 2020 to 2025 December. Now, if you click on the get data icon here, it will take some time, and then it will search through the data set that is available, and then it will give you a list of files that you can download them, along with a set of instructions on how to download it through, how to automate the download process through the command terminal, or you can just, manually download it by clicking on each of them one by one. Now, once you have downloaded a file, and since it's a netcdf file, it has multiple layers in it. Now, if you open that file in a GIS software like a QGIS that I am showing here, you'll see a lot of bands with, this weird looking names, but all of this are, represent a particular kind of AOD data. What we are interested here is a band called, with this acronym .ext.tau. And now this is the band which represents the AOD data at 550 nanometer, basically the same data that we get from, the same wavelength AOD data that we get from Modi's DBDT. So once you just select that, load it up, it should show something like this, and that is basically the data set. Anyways, but what we're interested is in making this process easier, and for that we have to go to the Google Earth engine, because this dataset is also available there, and the code for accessing it and visualizing it is pretty much similar to the IAC data that I showed earlier. The only thing that we have to change is the image collection. We are using a different image collection because it's a different data set, and the band name, which can vary across the data sets. Uh, Same way, you can visualize it as well, pretty much the same code as the previous one. And this is how get a reanalysis data like a Mira 2. You can also use the same code, by just changing the image collection and the bands, and you can get Sentinel-2 AOT data as well. However, you have to keep in mind that Sentinel-2 AOT data is just a byproduct of their surface reflectance algorithm and is not meant for any operational AOD use. So use it with care, so to say. Anyway, so these were the satellite derived AOD products. We looked at 3 of them. Now we will see how to access a ground-based AOD product called Aeronet. So ground-based AOD measurements are only available for select locations. So they are point data sets, pretty much because we can only put instruments at a single point, right? Now, a natural question that comes in mind is why do we need ground measurement with limited coverage when we already have satellite-derived continuous AOD datasets like a reanalysis Mira 2 dataset? And the main reason for having this ground-based measurements is that we need a validation dataset, right? This ground-based measurements are pretty accurate, and we use it to assess or improve the accuracy of the algorithms which are being used to retrieve AOD from the satellite data. And that's basically the prime use of this kind of data sets. Anyways, to get to the AirNet data, you have to do a bit of work. So I have mentioned the website here. So we have to go to this NASA website. We have to select our AOD solar product, and then we have to click on the download tool in the sidebar here. So the AirNet data has different versions, and now these versions are based on the instrumentation and the pre-processing that has gone into it. Currently, we have the version 3, and that's what we are going to use in this presentation. Now in version 3 product, you have 3 levels of AirNet data. So level, I have highlighted that in red here. So level 1 is the raw instrument measurements. Level 1.5 are the measurements that have been screened for cloud contamination and other quality controls. And then we have a level 2 product, which has undergone further quality checks and is possibly the most accurate AirNet measurements available. However, level 2 data is not available for all the locations and for all the dates. So the most popular AirNet data that we generally use for research purposes is level 1.5, and that is what we are going to do here anyway. So once you have clicked on the download data, this portal opens up. Now here you can select the location, you can select the date and the other parameters. And for instance, in this example, I am selecting a location called Kanpur. So Kanpur internet site in India is pretty unique for a reason that we have had the longest internet record for this site. So basically, you just give it the date, you select the products, and you submit your request. Now, once you have submitted your request, the server checks for the data that you selected, and if it is available, then you get a link to download the file. Now, it's possible that the date and the location that you have selected, there is no data for it. And in that case, you may not get anything. So, it's a bit of a trial and error. Then you can open up that file in Excel and, do a lot of pre-processing to clean and organize the data. So since AeroNet measurements are sometimes available at 5 to 15-minute intervals, you also have to do something called temporal averaging. And this is done to ensure that you are taking the atmospheric conditions, the average atmospheric conditions into account. and we're not just relying on the instantaneous AOD measurements, which may be inaccurate as well. Now, this entire process of downloading the data, cleaning it, organizing it, it can take anywhere between 15 to 20 minutes for each site and each date, and is very tedious and time consuming. Fortunately, there's a quicker way to do this. So, as part of my master's with Manu ma'am, we integrated an AeroNet extraction module in the IAOD software. That can do this entire thing for multiple sites in a matter of few seconds. So this window shows how it looks like. You can see you can provide pretty much all the information, and it will automate the task for you. Now, if you need more information on how to access this tool, I would recommend please contact Manu ma'am directly. So this kind of sums up our first part of the presentation, where we looked at the data sets, some of the common data sets, and how we can access them. Now, in part two, we'll have a brief look at the IAOD software. We won't go into much details because of the time limitations, but I'm hopeful that this short walkthrough gives you enough idea about what it does. So, as I mentioned before, during my master's at IIRS during 2021-23, I was working with Manu ma'am to develop a simple iterative algorithm for AOD retrieval from satellite images using higher wavelength bands, particularly RED and NIR. So we developed this software as part of that to make it easy for others to use our algorithm without having to go through all the codes and the steps. So in this software, the entire backend and processing is automated. We do require certain user interventions, but those are mainly for providing the input data and adjusting the two iterative parameters called the asymmetry and single scattering albedo. So this is basically the only step where some kind of user intervention is required. This flowchart shows where it is required. Of course, it's bit complex to go in all the details, but I have linked the paper that explains this process in great details. So be sure to check it out. Now, what I will do is I will show you a short time lapse of the ICE AOD software, how it looks when you are running it. Now, keep in mind that this video is bit speeded up, to fit the presentation mode. But again, I'm hopeful it should give you enough idea about the interface. And once again, if you do have any questions about access, how you get this tool, do contact Manu ma'am. So I'll play the video now. I'll just go through this. I'm not explaining this, this steps because uh, they are pretty technical. I don't think we have enough time for that. But again, please go through the paper. It, I've, I think I've done a pretty good job there explaining it, hopefully. So this is how the interface for the AOD looks like. You just select the sensor. We have capability to retrieve AOD from 5 sensors: Landsat 8 and 9, Sentinel-2, LEAS-3, AWIPS, and OCM-2. And then you can retrieve AOD at pretty much all the bands. You can also do a bit of pre-processing. For instance, if you have Landsat data and you have a QF pixel, which is the quality pixel metadata file, you can also apply cloud coverage corrections and things like that, filtering. And the user intervention is mainly required when you are selecting the asymmetry parameter. Again, in the software itself, we do have a bit of explanation about what it is and how you can select an appropriate parameter. It also, of course, has the AeroNet module integrated in it, so you don't have to go outside. And the I mean, this is of course speeded up, but it generally takes around 45 minutes for for a 250-meter Sentinel-2 resampled scene to get completed. So that may give you a brief idea about how quick this process is. And I guess that is all from my side. I put the QR code again here in case you missed the presentation or some part of it and you want to go through it again. Thank you.
All right. Thank you, Akhilesh. Can we have some questions? I'll be keeping only those which are related to the demonstration. The physics part of it we can take up with the respective faculty. Okay, so one question, Akhilesh, is how can QGIS be integrated with satellite data from MODIS? Maybe they want to know how satellite data is to be used in QGIS.
Okay, so QGIS, I mean, I don't think there's a direct, there's a direct plugin or module where you can directly pull in the MODIS data in QGIS. However, if you do have the MODIS data downloaded, for instance, you have it in a GeoTIFF file or you have it in NetCDF file, you can load them up, in QGIS. You can do pretty much everything that you can do with other files. So I think QGIS is a platform where once you have the data, you can work with it. It could be Modis data, it could be any other data as well. So nothing particular in there, I guess.
Related to that, I think you have already covered, but briefly you can give a small overview. What is the standard workflow for importing and processing MODIS level 2 data in QGIS?
Okay, so I will just go through that steps again, I guess.
Yeah, just briefly you can cover them again.
Yeah, I think we have a bit of time, so that's good. Okay, let me share it again. Right. Okay, so I'll go a bit slowly, I guess, this time. Basically, you go to this DAC portals. There are different DAC portals. The Modis data is available from something called a LADS DAC. This is the website here, and you can just go to find data, and this kind of opens up automatically. Now you can just search the name if you know the product already, or you can apply a filter like we have here under the atmosphere category, just aerosol. And if we just scroll down, we'll ultimately see the Modis products that are available. We just have to select one of them. Now the use case of which ones to choose pretty much depends on you. For instance, we know that the 10-kilometer product, Modis product, is a bit better over Indian subcontinent compared to the 3-kilometer product. So if you are working in the North India part of it, where we do have a bit of aerosol load, it's better to go with 10-kilometer product, for instance. And then pretty much you see next, and you can put your date range. You can select multiple dates. You can select one date. You get then you put a bounding box for the region for which you want the data. For instance, I am shown here, like if you want to get the data for the entire Indian subcontinent, and then you just get a list of the files that are available. If you see here, they are originally in something called an HDF file format, but then Modis does allow you to get that data in a different file format like GeoTIFF, which is much easier to work with. So in the post processing or the final step, you can just change it to GeoTIFF. You can also combine the files. If you have multiple files for the same date, you can mosaic them, and you get a email like this once your order has been processed. Now you can see there are three ways to download it. If you're comfortable with using wget tool, you can automate the entire downloading process through the command terminal, or you can just download them manually from the list that is at the very bottom that you can see. And once you have the file, they are just a bunch of geotiff files. So you use them as you use any other file. You just open them in QGIS like a raster data, and that's pretty much it, I guess.
All right. One last question we can take. I think you've discussed the Giovanni website. So one question is some views on Giovanni for downloading aerosol optical depth products.
Okay, so I in my presentation I haven't included Giovanni, uh, but is there anything specific about the Giovanni website that I can
No, this
answer?
is it's like they might be wanting to download the reanalysis data products. You might have
Mhm.
showed some Mera products there in these
Oh,
slides.
right.
Yeah, yeah. So just you
So,
can briefly, yeah, touch upon.
okay, okay, sure thing. So, uh, for Mera 2 data, we have two ways to download it. I mean, at least what I have shown. One is through the Earth data portal, which I guess looks pretty similar to the Giovanni. I don't remember that website. So, basically, it opens a portal like this, where you select your product. Now, in my case, Mera 2, I'm selecting Mera 2 data because it's available in this portal, and it has different data sets. Some are available at 1 hour, others are at 3 hours, some are monthly, and each of them has a data code. Now, if I go back here, you see there's a documentation here, and this one has a list of all the data code and what kind of data it is. So you just go with one of them, and then you click on the subset and get data here. There's an icon below which opens up this portal. I'm guessing Giovanni should look something similar since they share the same backend.
Yeah.
And here you can download the original file or subset it or whatever you want to do the processing.
Yeah, it's just another interface. Dr. Akhilesh has shown you GESDISC interface for downloading or fetching the Merato data. Similarly, you have Giovanni portal also, where similar reanalysis data sets are available to download. You can give whether you need it at hourly basis or daily basis or monthly basis or annual basis, etc. So the preface, the outlook also looks quite similar, and the data fields that you need to select is also quite similar. Yes. So thank
Exactly. Yeah.
you.
Thank you.
Yeah. Thank you, Akhilesh. I sincerely appreciate you. You are a distinguished alumnus of our institution. You've conducted an engaging and highly informative hands-on training session on the aerosol products and retrieval software and the methods of accessing these data resources. I also sincerely appreciate your thoughtful initiative of providing a QR code containing the training materials and relevant resources, which could enable the participants to follow the session seamlessly. Thank you so much for joining us. And I would also request all the participants as well as you to please join us at 4 o'clock for the valedictory session. This will be chaired by Dr. R.P. Singh. He is Director IIRS. So we will have his valedictory address for this 2 day long workshop, as well as our guest speakers who have joined us in this workshop. We will also try to have them on board there. Thank you so much. Thank you.
Thank you very much, ma'am. It was my pleasure to be here. Thank you.
Singh, Dr. Hina Pandey, Head PRST, Dr. Harish Karnatak, Head GITDL Department, and we also have joined a guest faculty with us, Dr. Neeraj Rastogi and Dr. Aditya Vash, as well as Mr. Akhilesh Kumar. So we begin the session, and for that, I request Dr. Hina Pandey. Madam, please provide the welcome and the opening remarks.
Thank you, Dr. Manu. Respected Director IIRS, Dr. Harish Karnatak, Head GITDL Department, and Dr. Manu, the course coordinator of this two-day workshop, coordinators of our nodal centers across the country, esteemed resource persons, and all the participants who've joined us online. Good evening and a very warm welcome to this valedictory session of the two-day workshop on aerosols. It is indeed a pleasure to be here at the closing of this workshop that over the past 2 days has brought together students, researchers, professionals from academic institutions, government departments, and organizations spread across the country. They were all connected by a shared interest in the tiny particles which we call aerosols that shape our atmosphere in different ways. Aerosols occupy a very important place in atmospheric science. They are minute and easy to overlook, yet they influence our climate, the air we breathe, the radiation balance of the planet, and human health in ways that we are still working to quantify. That is precisely why a forum like this matters very much. Over these 2 days, the speakers have taken you across a considerable canvas. Uh, Aerosol physics and optics, forcing and boundary layer dynamics, aerosol chemistry, health impacts, ground-based instrumentation, the physics and retrieval of aerosols from remote sensing platforms, aerosol modeling, and hands-on sessions that let participants work directly with the data and the techniques. This, I feel, was a very ambitious canvas for the 2 days, and I'm glad that the course coordinator attempted it. I would like to thank our resource persons for their time and sharing their thoughts with the participants. The Nodal Center coordinators for organizing the participation at their institutions, and the IIRS Distance Learning Program team for technical support that kept these sessions running smoothly as they did throughout the 2 days. My particular appreciation goes to Dr. Manu Mehta, the workshop coordinator. To the participants, I would like to say that even though aerosols are very small, tiny particles, but they have huge impacts and consequences for climate, air quality, and human health. And the questions in this field remain genuinely open. So there are several research questions still open after you've had all these discussions. We would suggest that let this be a beginning rather than a conclusion. And if a session here has suggested a research question or a data set that you feel would be worth examining, please pursue it. We hope that this workshop has been able to ignite your curiosity on the topic, and some of you will use this learning as a stepping stone for more rigorous research and studies. That is what would make this effort worthwhile. And with this, I wish all of you the very best for your future research endeavors. Thank you so much.
Thank you, ma'am. Thank you for such important comments and setting the tone of this concluding session. Now, I request Dr. Harish Chandra Karnatak, Head GITDL Department, to kindly brief about the activities of IIRS Distance Learning Program. Sir, please.
Thank you, Dr. Manu, Director IRS, Dr. R.P. Singh ji, Dr. Hina Pandey Madam, Head PRSD, Dr. Manu, course coordinator for this 2 days workshop, and dear course participant. First of all, I would like to congratulate all of you for successful completion of this 2 days workshop. This workshop we have conducted under IRS distance learning program. And IRS distance learning program we have started sometime in 2007 after launch of ISRO's EduSat satellite. The major objective of that program that time was basically to reach the unreached area in the country. So we have started very small startings where around 12 universities or academic institutions connected with us. And today, after around 20 years journey, so around 4,500 institutions are connected with us. And every year we are conducting around 35 online courses on different topic of space science, space technology, space applications, including the remote sensing Earth observation. So uh, every year around more than 150,000 students are connecting with us, and a mass scale outreach program is being conducted. And these programs are conducted in two modes. One is as an individual participant, you can join, and also you can join through the nodal centers. As I told you, around 4,500 nodal centers are there in the country, and this number is continuously increasing. If any student is feeling that these courses are important and interesting for them, they can request their college or their university to become the partner in this IRS outreach activity. So this is completely free of costs, available for the institutions, are also available for the student community. As we have seen in this course itself, around more than 10,000 participants have registered for 2 days workshop. This was a very short duration program. So in fact, to get a certificate for workshop completion, only we are recording the attendance for short duration programs. Otherwise, you have to maintain the 70% attendance and also score the 50% marks in your online examination. All these programs we are conducting through a learning management system developed by IIRS team. It's called ISRO e-class platform. And you can create your account, and all the videos or the contents, whatever are delivered by the experts here, will be available as archive under your login. You can watch this video anytime, and otherwise also you can download some of the content in the form of the PPTs or maybe some reading material from the website for your future reference. I once again thanks all the participants for showing their interest in our distance learning program. You please see our the course calendar, which is available in our website. You can select the course or workshop as per your interest, and you can participate. So I welcome all of you for these upcoming courses also. And these courses are available without any course fee. So this is a very important point for the participant. And you can also attend these courses through another platform called Massive Open Online Course. There the recorded videos are available, and maybe large number of courses are also available there. So you can go through these courses as per your time or as per your uh, availability. In fact, in the weekends or in the night time also, you can go through these courses. So thank you very much for joining this 2 days workshop, and wish you all the best.
Thank you, sir. Thank you for apprising all our gathering here about the IIRS distance learning program. Now it's my immense pleasure to read out the workshop report. So, over the past 2 days, we successfully conducted this online workshop on aerosols, measurement, retrieval, and impacts. This workshop brought together eminent scientists, academicians, researchers, professionals, and students from across the country to deliberate on various aspects of aerosol science, ranging from fundamental principles to advanced applications. So there were the 2 days were focused on two different aspects. Day one was focused on understanding the aerosols, their interactions and impacts. And second day we have devoted towards their measurement aspects, their retrieval challenges, as well as the modeling. So the workshop began with Dr. Yogesh Kant, Head Atmospheric Science Department, IIRS, who provided a comprehensive introduction to aerosol physics and optics, covering aerosol formation mechanisms, scattering, absorption, and particle size distributions. Dr. Naren Singh, scientist from IIRS Nainital, he discussed aerosol radiative forcing, aerosol boundary layer interactions, vertical distribution of aerosols, and their influence on weather and climate processes. This was followed by a session by Professor Neeraj Rastogi. He is professor in Physical Research Laboratory, PRL Ahmedabad. He is currently serving as president of ISTA, Indian Aerosol Science and Technology Association. And sir has also joined us online here in this session. He has delivered an insightful talk on aerosol chemistry, including chemical composition, transformation pathways, and source signatures. We also had a very important session by Professor Sagnik De. He is Institute Chair Professor in IIT Delhi and coordinator of the Center of Excellence for Research on Clean Air. Professor De is one of India's leading experts on the air quality climate health nexus. He highlighted the impacts of particulate matter on human health, aerosol health linkages, air quality monitoring, exposure assessment, and the role of satellite observations in health related studies. So the second day focused on measurement techniques, remote sensing and modeling. Dr. Aditya Vash, he's Associate Professor Ahmedabad University. He was also associated with SAC Ahmedabad and VSSC. He's also joining us online right now. He introduced the participants to a wide range of aerosol observation systems and working principles of several optical, physical, and chemical properties of aerosols. So he's also developing a low-cost aerosol sensors in his lab. Then I have discussed the physical basis of aerosol remote sensing, the signatures of aerosols in terms of wavelength, viewing geometry, polarization, and the retrieval methodologies for surface, columnar, and vertical aerosol distributions, as well as touched upon the recent advances covering machine learning based retrieval approaches. Dr. Narendra Ojha is scientist at PRL Ahmedabad. He has also joined us online. He subsequently presented various aerosol modeling frameworks such as WRF-Chem, CMAQ, GEOS-Chem, highlighting emission inventories, interactions, transport processes, and emerging AI/ML-based modeling approaches. The workshop concluded with a practical hands-on session conducted by Mr. Akhilesh Kumar. He is doctoral researcher, University of New South Wales, Sydney. He is also an IIRS alumni, where participants gained experience in downloading, visualizing, interpreting aerosol information from satellite observations, aeronet measurements, and reanalysis data sets also. So linking the theoretical concepts which we covered with the practical data analysis workflows. Especially, I would appreciate him. He gave a thoughtful initiative of providing a QR code, and the participants could parallelly work on the hands-on session. So overall, the workshop provided the participants with a holistic understanding of aerosol science, encompassing their physical, optical, and chemical characteristics, measurement methodologies, remote sensing retrieval techniques, numerical modeling frameworks, and their impacts on climate, environment, and human health. Especially, I'm happy that we received a very enthusiastic participation, thought-provoking questions, and lively discussions throughout all the sessions. With this, I conclude the workshop report, and we have senior faculties here. Sir, if anyone would like to have some comment on the workshop session, Professor Rastogi, you can.
Yeah, okay. So first of all, good afternoon, everyone. Director IIRS, Dr. RP Singh, and all other members, my friends, Aditya Vesh, Narendra Ojha, and all. So I really appreciate the effort which IIRS is putting in disseminating the knowledge to the younger generation. I see that means I gave 2-3 times the lecture, but I see often means I follow this YouTube channel and I see that you do this kind of thing very regularly, which is highly appreciable. And I think it should be continued, and we should try to add more and more newer things and things, very specific things, so that student can go much in details. So instead of covering the broad thing, take a further smaller topic and go in deep. So that will be another resource available for the students. Thank you.
Thank you, sir, for the insightful comment. Okay. Professor Vash, Dr. Ojha, if you'd like to give a brief comment.
Yeah, sure. Good afternoon, and thanks very much for this opportunity. This was a wonderful experience for me interacting with, wonderful audience. Thought-provoking questions were also there. I know this platform of online education and online learning is very, very important, but probably in near future, if you can also have, in-person workshops, very intensive workshops like this for selected audience, obviously that will be, I think, very wonderful.
Yeah, sure. Thank you. Thank you, sir. Dr. Oja?
Yeah, thank you. Good afternoon, sir, and thank you, Manu. So yeah, as Aditya said, sometimes we should also do some selected offline workshop where we can give more training on numerical modeling and uh, instrumentation. So that will be more useful. But as of now, I saw that a lot of very good participation was there, and I was quite impressed with the kind of questions that audience was asking. So although it was online mode, the participation was very good and interaction was very thought provoking. Thank you for this opportunity.
Thank you, Dr. Oja. Now is the time that we are eagerly waiting for. Sir, I request Director IIRS for the valedictory address. Sir, please.
Thank you, Dr. Manu. Good evening to everybody. Dr. Harish, Karnataka, Dr. Hina Pandey, ma'am, Dr. Manu, Dr. Neeraj Rastogi ji, Aditya Vaishnav ji, and Narendra Ojha ji, and all the participants of this program. So first of all, congratulations to all the participants for completing this 2-day workshop on aerosols measurement, retrieval, and impacts. And at the same time, I'm thankful to all the faculty members for their valuable participation and giving talks. When I was seeing this workshop details, I found is one of the interesting workshop which IRS does. Although IRS has a culture of carrying out many such kind of workshop as a part of the capacity building and outreach. But here I am seeing more than 10,000 people participated. There's one element of it. So it shows the interest in the country about this topic. And the topic has become really very important and being taught at various places. It shows like that many people are interested. And second, I take opportunity to congratulate the coordinators, the team members who has planned this. I see a beautiful, what you call, lectures being planned, which covers most of the required topics of aerosol, call it physics and optics, boundary layer, chemistry, health, whatever I'm seeing, the ground, the satellite, modeling, and so on. So, in my opinion, it is one of the important workshop I have seen where such a good canvas of talks has happened. And more importantly, the faculty members who comes from the various reputed institutions and the expertise in the field, and they agreed to participate. So in total, I see I hope that participants would have really enjoyed these talks and learned. And as we heard from the comments from the some of the faculty also that you had a good interaction sessions. So it's a good sign for any workshop. And certainly, we'll take your comments, feedbacks, and see that more such things happens in future, as you suggested, so offline, some selected discussions should also happen because this subject is growing, evolving with the time, and particularly its satellite measurement part is growing much more, and the requirement is also like that. As the human populations are increasing, obviously things are getting polluted and polluted. India, particularly northern plain, we all know is highly polluted, and to see this observation, of course, you require satellites, and that's how all the satellite measurements started very early in 90s with the help of MADIS was the one of the starting satellite. There were series of satellites, Terra and Nora and what you call Aqua, and then later on the Calypso, then I think the MISR, and then Parasol, Polar. I'm just remembering the sequences because I used to work with them a decade ago. And I mean, there has been a beautiful development in this field. And I'm quite confident that Dr. Mani would have taught you all those basic principles of detection and the aerosol which looks tiny. Uh, by now, you know they are not tiny. They have a big impact in terms of their forcings. So it's really very, I mean, I would say interesting to know how things which is not seen visibly through our eyes has a huge impact to our health, to the climate, and to our ecosystem as a whole. And not only today, I mean, tomorrow we have to be more worrying about it. So ultimately, we have to have a dedicated systems for measuring this kind of thing. We have to have the constellations of measurements together, and it can be not only from one institute or one country. It has to be done from the cooperation of international participants, and I hope many such things are being planned in future also. Polarization measurements has to play important role, because end of day, either you take only reflectances or have a multiple viewing things. Unless you take the help of polarization, the ambiguity remains there, because the land, the what you call brightness over science, particularly, or the brighter objects, start looking very similar to what the aerosol looks. So to avoid them, you have to have polarization measurement, which makes the differences, because the land surfaces obviously becomes darker in polarized sense as compared to the aerosol, and that the basic premise. Already parasol and Polder has tested it. In future, there will be such more missions. India itself is planning one G20 satellite for G20 countries. And I assume that this topic and the knowledge regarding this will be very useful to the participant, either they are researchers or their students, or the teachers, because I see that the subject will have more and more importance in the coming years. And I'm happy that IRS is taking initiatives in all the spheres of knowledge which is emerging from satellites, and which is beneficial to society. So I take this opportunity to again thank the faculty members, the coordinators, and the participants to be part of this workshop. And my best wishes to you. Thank you very much.
Thank you, sir, for your enlightening and visionary remarks. Now, I take privilege to propose a formal vote of thanks. First of all, I would like to extend my sincere thanks to Director Sir for his kind approval and encouragement in every step for conduction of this course. Thanks are due to Ms. Shifali Agrawal, Dean IIRS, for all her support. My sincere thanks also goes to Dr. Anil Kumar, Group Head GTOP Group, for his guidance and support during the conduction of this course. Special thanks are due to Dr. Harish Karnatak, Head GITDL, for accommodating this workshop in the distance learning mode. I am sincerely thankful to Dr. Hina Pandey, Head PRST, for her constant guidance and support for this workshop. Yeah, I'm extremely thankful to all our speakers, all our guest speakers, for agreeing to share their expertise for this workshop. I'm especially thankful to all the guest speakers who are joining us live right now in this session. Once again, I wholeheartedly thank you. Thanks are also due to all the DLP staff, Mr. Janardhan, Mr. Ashok, Mr. Harsh, Mr. Sajid, for all their support. Last but not the least, I would also like to thank all the participants who have joined this workshop. Considering that this workshop would just has marked an enthusiastic beginning, we hope that you would continue exploring further this domain and be in touch with us. Thank you.
Then, sir.
Thank you, sir. Thank you, ma'am.
Everybody.